the universe did not start quietly. Before there were galaxies, before there were stars, before even time itself ticked its very first second, something extraordinary happened. The universe erupted into existence in a single, unfathomable event that we now call the Big Bang. From that instant, space began stretching, matter took form, and the seeds of everything we know were sown. Yet for all the progress science has made in understanding what followed, the great mystery still lingers at the very heart of it all. What caused it? What force, what spark, what unknown reality set off the chain reaction that would give rise to billions of galaxies, to planets, to life, and to us? Before we embark on the journey, tell us where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a fascinating journey to the beginning of time. The Big Bang Theory is the main explanation of how the universe came into being and how it has been spreading out ever since. It says that the universe began as an extremely hot, tightly packed point and has been growing larger with time. Scientists use different versions of the Big Bang idea to explain many important mysteries of space, such as why certain light elements like hydrogen and helium are so common, why there is a faint glow of energy spread across the universe called the cosmic microwave background radiation, and how galaxies and other huge structures formed. One major idea linked to the Big Bang is something called cosmic inflation. This means that, in the very first moments after the universe began, it spread out at an unbelievably fast rate. This quick spreading helps explain why the universe looks so smooth and even in all directions. A huge amount of scientific proof strongly supports the Big Bang theory, and today it is almost fully accepted by scientists. Careful calculations based on the universe's spreading suggest that the Big Bang happened about 13,787,000,000 years ago, which is thought to be the age of the universe. By turning back this spreading using the known laws of physics, scientists have found that the early universe was unimaginably hot and tightly packed. But they still do not have a complete theory that can describe exactly what happened in the very first moments of the Big Bang. As the universe grew bigger, it also cooled down, letting tiny particles come together and form atoms. These early atoms, mostly hydrogen with some helium and lithium, later clumped together under the pull of gravity, helped by an unseen force called dark matter. Over time, these clumps of gas turned into the first stars and galaxies. Studies of faraway exploding stars called supernovae show that the universe is not just spreading out, it is spreading out faster and faster. This shocking finding is linked to a strange force called dark energy, which scientists still do not fully understand. The idea of a spreading universe was first suggested by Russian scientist Alexander Friedmann in the year 1922. He worked out mathematical rules, now known as the Friedmann equations, to explain this spreading. A few years later, in the year 1929, American skywatcher Edwin Hubble gave proof by observation that the universe really was spreading. He found that galaxies are moving away from Earth, and the farther away they are, the faster they seem to move. This finding is now called Hubble's law. Apart from Friedmann and Hubble, Belgian scientist Georges Lemaître also suggested that the universe began from a single, extremely small and tightly packed point, which he named a primeval atom. This idea, suggested in the year 1931, laid the base for what is now known as the Big Bang theory. The strongest piece of proof supporting the Big Bang came in the year 1964, when scientists found the cosmic microwave background radiation. This faint glow of energy, left over from the early universe, matched the predictions made by Big Bang ideas. Its discovery convinced most scientists that another theory, called the steady-state model, which said the universe had no beginning and had always existed, was wrong. Even though the Big Bang theory explains many things about the universe, there are still some major puzzles that remain. Scientists are still trying to understand why there is more matter than antimatter, a puzzle known as baryon imbalance. They are also working to uncover the real nature of dark matter, the unseen stuff that seems to surround galaxies and hold them together. And maybe most puzzling of all, they are trying to figure out what dark energy really is and why it is making the universe spread faster with time. The Big Bang theory depends on three main ideas. The laws of physics are the same everywhere. the universe looks the same in all directions when looked at on a large scale, and the universe's matter can be thought of as a smooth, flowing substance. The idea that the laws of physics are the same everywhere comes from Einstein's theory of relativity. The second idea, called the Cosmological Principle, means that if you looked at the universe from any place, it would look the same in every direction when seen on a large scale. Lastly, a perfect fluid is a way of describing matter in space, assuming it flows without resistance, and that its pressure depends on how much matter is packed into a given space. At first, these ideas were only guesses, but scientists later tested them. For example, one way they checked the first guess was by studying something called the fine structure constant, which controls how light and matter interact. Their findings showed that this constant has barely changed, by about 1 part in 100,000, over the life of the universe. The second guess, the cosmological principle, was tested by looking at the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation is nearly the same in all directions, with changes of only about 1 part in 100,000. As of the year 1995, studies showed that on the bigger scales, the universe is mostly even, with any unevenness being at most about 1/10. The cosmological principle is very useful because it makes the rules in Einstein's theory of general relativity simpler. This leads to a mathematical model called the Friedmann-Lemaitre-Robertson-Walker metric, which explains the shape and spreading of the universe. By assuming that matter acts like a perfect fluid, scientists work out equations known as the Friedmann equations, which help predict how the universe changes with time. At the centre of these equations is a single important number, the mass-energy density. This number decides both the shape of the universe and how fast it spreads. One of the biggest steps forward in understanding the universe came when scientists figured out what the universe is made of. By studying the way galaxies move and how light acts in space, they found that the matter we can see, stars, planets, and everything that shines, makes up less than 5% of the universe. The rest is something unknown. About 27% is dark matter, an unseen substance that affects gravity but does not give off light, and 68% is dark energy, a strange force that seems to be pushing the universe to spread faster. Another key idea in Big Bang studies is the thought of particle horizons. Since the universe has a limited age and light moves at a fixed speed, there are limits to how far back we can see. Some light from the past simply has not had enough time to reach Earth yet, which makes what is called a past horizon, a border beyond which we cannot look. In the same way, because the universe is spreading and faraway objects are moving away faster and faster, some of the light we send out today may never reach certain faraway parts of space. This makes a future horizon, meaning there are some places in the universe that we will never be able to affect. Looking back at the very early universe, we find proof for a past horizon, but our view is also blocked by the fact that in its earlier stage, the universe was too tightly packed for light to move through freely. With time, as the universe spread, this horizon has moved farther and farther away. If the spreading of the universe keeps speeding up, we may also have a future horizon, meaning some parts of the universe will one day be forever unreachable. At the very start, according to the Big Bang theory, the universe was unimaginably hot and tightly packed together. Then, with time, it began spreading and cooling down, leading to the vast universe we see today. But the moment when everything began, the exact instant of the Big Bang itself, remains a puzzle that modern physics cannot fully explain. If we turn back time using Einstein's general theory of relativity, we reach a point where the universe was so tightly packed and hot that all our known laws of physics fail. This state, known as a gravitational singularity, says that the universe had endless heat and endless density at some time in the past. But what that really means is unknown, as general relativity alone is not enough to explain the extreme conditions of the Big Bang. Scientists believe that during these earliest moments, the effects of quantum gravity, an unknown branch of physics that joins quantum mechanics with gravity, would have been the main force. This strange phase, called the Planck epoch, happened within a tiny fraction of a second after the universe began, in the very first 100 quintillionth of a quintillionth of a second, about 10 to the power of negative 43 seconds. At this moment, the universe was unimaginably small, with a size of about 1.6 times 10 to the power of negative 35 meters, and its heat was around 100 undecillion degrees Celsius, which is 10 to the power of 32 Kelvin. Conditions were so extreme that even basic particles as we know them did not exist. Scientists are still searching for a theory of quantum gravity to fully explain what happened during this time. As the universe kept spreading and cooling, the first big change happened at 100 billion trillion trillionths of a second, which is 10 to the power of negative 37 seconds. At this time, something extraordinary happened. The universe went through a sudden and huge growth spurt known as cosmic inflation. Within an extremely short time, it spread out exponentially, much faster than the speed of light. This process smoothed out the fabric of space and greatly lowered the universe's heat by a factor of 100,000. It also helped explain why the universe today looks so even and balanced. Tiny quantum changes that existed during this time were stretched and made larger, later becoming the seeds of galaxies and cosmic structures. Shortly after, at around 1/1,000,000,000 of a trillionth of a trillionth of a second, 10 to the power of negative 36 seconds, another important event took place. One of the four basic forces of nature, the strong nuclear force, separated from the others, leaving only the electromagnetic force and the weak nuclear force still joined together. This time, known as the electro-weak period, set the path for more changes to come. By the time the universe was 100 billion trillion trillionths of a second old, between 10 to the power of negative 33 and 10 to the power of negative 32 seconds, cosmic inflation had ended. The size of the observable universe had grown by an unbelievable factor of 1 followed by 78 zeros. After this, the universe entered a stage called reheating, where energy from inflation was changed into matter and radiation. Temperatures became high enough to form a kind of hot, dense state known as a quark-gluon plasma, where the basic parts of atoms, quarks and gluons, could move around freely. At this time, the universe was filled with powerful energy where particles and their antimatter twins were constantly being created and destroyed in very fast crashes. However, a strange process called baryogenesis shifted the balance in favour of matter over antimatter. For every 30 million matter-antimatter pairs, just one extra piece of matter survived. Because of this, when all the antimatter was destroyed along with matter, a very small amount of matter was left behind. This extra bit of quarks and leptons later formed the galaxies, stars, planets, and everything we see in the universe today. Scientists still do not know why this uneven balance happened, but without it, our universe as we know it would not exist. These very first moments of the universe remain one of the biggest mysteries in science. While we have built strong models to explain what likely happened, much is still unknown, especially about the physics that ruled the very first instant of time. Future findings in quantum physics and cosmology may one day open the secrets of the Big Bang and show exactly how our universe came into being. As time moved on, the universe kept expanding, which made it less dense and cooler. This cooling meant that the energy of each particle was also dropping. During this process, the basic forces of nature took on the forms we know today. One major change in this process was the split of the electromagnetic force from the weak nuclear force, which happened in an extremely short moment, about 1/1,000,000,000th of a second after the Big Bang. Around 100 billionths of a second after the Big Bang, the universe's energy levels dropped to a range that scientists today can study using powerful machines called particle accelerators. By the time the universe was only a millionth of a second old, tiny pieces called quarks and gluons started joining together, forming larger particles known as baryons. These included protons and neutrons, the parts that make up atoms. Because there were slightly more quarks than their antimatter partners, called antiquarks, this caused an uneven result, more matter than antimatter. When the universe cooled even more, new proton-antiproton and neutron-antineutron pairs could no longer form. This caused almost all the leftover antimatter to be destroyed in a huge annihilation event, leaving only about one matter particle for every 100 million that first existed. A similar event took place about 1 second after the Big Bang when electrons and their antimatter twins, positrons, also destroyed each other. At this point, the universe was mostly filled with leftover protons, neutrons, and electrons, while most of the energy was carried by light particles called photons, along with a smaller number of neutrinos. A few minutes after the Big Bang, when the temperature had dropped to about 1 billion degrees, Kelvin, protons and neutrons began coming together to form the first atomic centers, mostly deuterium and helium. This process, called Big Bang nucleosynthesis, laid the base for the elements that would later make up stars and planets. This process, called Big Bang nucleosynthesis, laid the base for the elements that would later make up stars and planets. But most of the protons did not join and stayed as simple hydrogen centers, which later became the most common element in the universe. As time went on, matter started to play a bigger role in shaping the universe. About 50,000 years after the Big Bang, the pull of gravity from matter became stronger than the effect of radiation. Then, around 380,000 years after the Big Bang, the universe had cooled enough for electrons to join with atomic centers, forming neutral atoms, mostly hydrogen. This stage, called recombination, was a key turning point because it allowed light to move freely through space for the first time. The remains of this ancient light can still be seen today as the cosmic microwave background radiation. After recombination, small differences in thickness across the universe caused some areas to pull in more matter, leading to the formation of huge clouds of gas. Over millions of years, these gas clouds collapsed under gravity to form stars, galaxies, and the large-scale cosmic shapes we see today. The type of matter in the universe plays a big part in this formation process. Scientists group matter into four main types: cold dark matter, warm dark matter, hot dark matter, and baryonic matter, the kind that makes up us. Based on the most exact measurements, taken by the Wilkinson Microwave Anisotropy Probe, the universe seems to follow a model where cold dark matter is the main kind. Based on this model, scientists believe that dark matter makes up about 23% of the universe's total matter and energy, while baryonic matter makes up only about 4.6%. The rest is thought to be dark energy, a strange force that pushes the universe to expand. Scientists have found strong proof from two different sources: exploding stars called Type Ia supernovae, and the faint glow left over from the early universe, known as the cosmic microwave background, that show our universe is mostly made of a strange and unseen force called dark energy. This mysterious energy is believed to spread evenly across all of space and makes up about 73% of the total energy in the universe today. In the very early days of the universe, dark energy was likely present, but everything was packed much closer together. At that time, gravity was much stronger and acted like a brake, slowing down the universe's growth. But as billions of years passed and the universe kept expanding, matter became less dense. At some point, the balance changed. Dark energy started to beat gravity, making the universe expand faster instead of slower. Scientists try to explain dark energy using Einstein's theory of general relativity, where it shows up as a math idea called the cosmological constant. But they still do not know exactly what dark energy is made of or how it works. Experts are studying its possible features through both watching the universe and using math and models to understand it. They are also trying to connect it to the standard model of particle physics, which describes the basic particles and forces in nature. The way the universe has changed since its first moments can be described using a science model called the lambda cold dark matter model. This model brings together two important theories: quantum mechanics, which explains tiny particles, and general relativity, which explains space, time, and gravity on a large scale. But what happened before the universe was 1/4,000,000th of a second old, that is, 1 divided by 1,000 trillion seconds, is still a great mystery. There is no simple test or theory that can fully explain that time. Understanding the very first moments of the universe is still one of the greatest unsolved puzzles in physics. The term Big Bang was first used by the British astronomer Fred Hoyle during a BBC radio talk in March of the year 1949. While talking about different ideas of how the universe began, Hoyle described one idea by saying that all matter in the universe was created in one Big Bang at some point in the far past. At first, people did not quickly start using this word, and it only became popular in the 1970s. Many people think that Hoyle used the phrase Big Bang as an insult because he personally supported a different idea called the steady-state model, which said that the universe has always existed and would continue forever, without a beginning or end. But Hoyle later said he did not mean it in a bad way. He said he only wanted to create a strong image that would make the differences between the two ideas clear. Some historians, such as Helge Krag, believe that there is little real proof that Hoyle was trying to mock the theory. Interestingly, the term Big Bang itself is somewhat misleading. It makes people think of an explosion, but the real event was not like a usual explosion that happens in one place and spreads outward into empty space. Instead, it was the whole universe itself growing from a super hot, super dense state. Some scientists also pointed out that the word bang makes people think of a loud sound, but sound waves cannot travel through empty space, making the name even less correct. But even though people have tried to find a better name, none have lasted. Long before the phrase Big Bang was used, scientists were already making findings that pointed to the universe's growth. In the year 1912, an American astronomer named Vesto Slipher was the first to measure something called the Doppler shift in light coming from faraway galaxies, which were then called spiral nebulae. He found that almost all of these nebulae were moving away from Earth, though at the time people were not sure if they were separate galaxies or part of the Milky Way. Then, 10 years later, in 1922, a Russian mathematician and physicist named Alexander Friedmann used Albert Einstein's equations of general relativity to show that the universe might not be fixed. It could be growing or shrinking. This idea was shocking because even Einstein himself thought the universe was unchanging. Another big step came in the year 1924, when American stargazer Edwin Hubble showed that the spiral nebulae were really other galaxies far beyond our own. He used the Hooker telescope, which was 100 inches or 2.5 meters across, to measure how far away these galaxies were. A few years later, in the year 1929, he made an even bigger finding. The farther away a galaxy was, the faster it was moving away from us. This link between distance and speed became known as Hubble's law, and was the first real proof that the universe was growing larger. At nearly the same time, in the year 1927, a Belgian scientist and Catholic priest named Georges Lemaitre also reached the idea that the universe was growing. He even guessed the link between distance and speed that Hubble would later confirm. But Lemaitre went even further. In the year 1931, he suggested that if the universe is spreading out, then at some point in the past, everything must have been packed into a single, unimaginably tiny and heavy point. A primeval atom, as he called it. This idea laid the base for what we now call the Big Bang theory. In the early 1920s and 1930s, most scientists did not like the thought that the universe had a beginning. The main view was that the universe was endless, without a starting point. Some even thought that saying the universe had a beginning sounded too much like religious stories of creation. The well-known British space scientist Arthur Eddington strongly opposed the idea of a beginning, calling it disgusting, because it suggested that matter had not always been here. Many other scientists supported the steady-state theory, which said that new matter was always being made as the universe grew, keeping everything looking the same over time. During the 1930s, other possible explanations were tried. Some scientists said that the universe went through cycles of spreading out and then shrinking back, while others, like Fritz Zwicky, came up with ideas such as the tired light thought, which said that light from faraway galaxies lost energy over time, making it look like they were moving away. After the Second World War ended, two main competing ideas appeared. Fred Hoyle kept supporting the steady-state theory, where the universe was endless and always looked the same, with new matter forming as space spread out. On the other side, scientists like George Gamow supported Lemaitre's growing universe idea and built on it. Gamow worked with Ralph Alpher and Robert Herman to form a theory explaining how elements like hydrogen and helium formed in the young universe. These same scientists also said that if the universe had once been incredibly hot and heavy, there should still be a faint glow left from that time, what we now call the cosmic microwave background. Though the Big Bang theory was still argued over for many years, later findings, including the discovery of this cosmic background in the 1960s, gave strong proof that the universe did have a beginning. Over time, what started as an idea many disliked became the most widely believed explanation for how the universe began. And it all started with a simple phrase, one that Fred Hoyle never meant to become famous: the Big Bang. It is quite surprising that the name Big Bang, which is now widely used to describe how the universe began, was actually made up by someone who did not believe in the idea. In March of the year 1949, British stargazer Fred Hoyle, who supported a different idea called the steady state model, used the words Big Bang during a BBC radio show. He meant it in a mocking way, but the name stayed and became the popular way to talk about the theory put forward by Belgian scientist Georges Lemaitre. For a while, scientists were split between these two competing ideas. However, as stargazers gathered more proof, especially from radio wave studies, it became clear that the Big Bang theory was the stronger explanation. The biggest turning point came in the year 1964, when two scientists, Arno Penzias and Robert Wilson, by chance found what is known as the cosmic microwave background. This faint glow of energy, spread evenly across the sky, was exactly what the Big Bang theory had said would be left over from the birth of the universe. With this finding, most scientists finally accepted the Big Bang as the best model for explaining how the universe began and grew. In the late 1960s and early 1970s, brilliant thinkers like Roger Penrose, Stephen Hawking, and George Ellis published powerful studies showing that, based on Einstein's ideas, the universe must have started from a singularity, a point of endless heaviness and energy. Then, over the next 2 decades, space scientists worked hard to improve the Big Bang model and solve leftover puzzles. In the year 1981, scientist Alan Guth brought forward the idea of cosmic inflation, a time of incredibly fast growth in the very first moments of the universe. This idea helped explain many riddles about the shape and sameness of the cosmos. During this time, 2 main arguments kept stargazers busy. One was about the exact value of the Hubble constant, which measures how fast the universe is growing. The other was about the total amount of matter in the universe, which was thought to decide its final fate. At that time, scientists did not yet know about dark energy, which would later change our whole picture of cosmic growth. Since the late 1990s, there have been amazing steps forward in our knowledge of the universe, thanks to better telescope tools and space-based watchers. Satellites like the Cosmic Background Explorer, COBE, the Hubble Space Telescope, and the Wilkinson Microwave Anisotropy Probe, WMAP, have given exact readings of key parts of the universe. Perhaps the most surprising finding came when scientists learned that the universe's growth is not slowing down, as once thought, but is actually speeding up, an effect now blamed on the strange force called dark energy. Today, the Big Bang theory is still the best explanation for how our universe came to be, and researchers keep uncovering new and thrilling details about its beginning and fate. The Big Bang theory gives a clear explanation for many of the wonderful things we see in the universe. It helps us understand why certain light elements like hydrogen and helium exist in certain amounts, why we can still see a faint glow called the cosmic microwave background, how galaxies are arranged in huge groups, and why they seem to be moving away from us as shown by Hubble's law. These key pieces of proof, often called the 4 pillars of the Big Bang model, strongly support the idea that the universe started from a single point and has been spreading out ever since. One of the first signs that the Big Bang theory was right came from the finding that galaxies are moving away from us, which we can tell by looking at how their light is stretched into longer redder waves, a happening called redshift. Another major step was the discovery of the cosmic microwave background, a faint signal left over from the young universe. Scientists also proved that the amounts of light elements in space matched the guesses of a process called Big Bang nucleosynthesis, which explains how these elements formed in the universe's first moments. In recent years, stargazers have gathered even more proof by studying how galaxies form and how huge cosmic structures are spread across space. To fully explain the Big Bang, scientists have put forward some strange ideas, including dark matter and dark energy. Dark matter is believed to make up most of the universe's weight, yet we cannot see it directly. We only notice its pull on galaxies and gravity. Many tests are going on to find out what dark matter really is. Dark energy, on the other hand, is thought to be the cause of the universe's fast growth, but what it truly is remains unknown. There are also other puzzling questions, such as why small galaxies act differently than expected, and why the centres of galaxies seem to have more dark matter than our models suggest. When we look at faraway galaxies and quasars, we see that their light has shifted toward the red end of the spectrum. This redshift happens because the universe itself is spreading out, stretching the light waves as they travel through space. If we measure how much the light has shifted and compare it to how far away these objects are, we find a clear pattern known as Hubble's law. This law tells us that galaxies farther away from us are moving away faster than those that are closer. The idea that the universe is spreading out was first guessed in the early 1920s by scientists like Alexander Friedmann and Georges Lemaitre. It was not until the year 1929 that Edwin Hubble gave real proof through watching the skies, changing our understanding of the universe forever. One way, based on studying the cosmic microwave background, gives a lower number, while another way, based on measuring distances to galaxies, gives a higher number. Scientists are still trying to figure out why these two numbers do not match. One of the biggest finds that confirmed the Big Bang theory happened by accident in the year 1964. Two scientists, Arno Penzias and Robert Wilson, were working with a radio antenna when they came across a strange background noise that seemed to come from every direction in space. This turned out to be the cosmic microwave background, leftover heat from the universe's earliest moments. Their find matched guesses made by other scientists in the 1950s, giving stronger support to the Big Bang theory. Because of this, Penzias and Wilson won the Nobel Prize in Physics in the year 1978. The cosmic microwave background is a faint glow left over from a time when the universe was extremely hot and dense. At that time, space was filled with a thick fog of charged particles, which made it impossible for light to move freely. About 372,000 years after the Big Bang, these particles joined together to form neutral atoms, making the universe clear for the first time. The light from that moment is what we now see as the cosmic microwave background. In the year 1989, NASA sent a satellite called COBE, short for Cosmic Background Explorer, into space. It made two major finds. First, in the year 1990, it proved that the cosmic microwave background had a perfect blackbody spectrum, just as expected. Then, in the year 1992, it found tiny temperature changes across the sky, small differences that later grew into galaxies and stars. These finds were so important that John Mather and George Smoot won the Nobel Prize in Physics in the year 2006. In the years that followed, experiments on the ground and on balloons gave even more exact measurements of the cosmic microwave background. In the year 2001, an experiment called Boomerang measured the pattern of these small changes and showed that the universe is almost flat in shape. Then, in the year 2003, data from the Wilkinson Microwave Anisotropy Probe gave the most exact numbers yet for key cosmic details, helping improve our knowledge of the early universe. In May of the year 2009, the European Space Agency sent up the Planck space probe, which gave even clearer measurements of the cosmic microwave background. Many other experiments, both on Earth and in space, still study this faint glow, giving us deeper knowledge about the beginning and growth of the universe. Although the Big Bang theory explains a lot, many mysteries remain. Scientists are still trying to understand dark matter, dark energy, and the exact details of what happened in the first moments of the universe. With new tools and ongoing study, we may one day uncover the full story of how our universe began and what its final fate might be. Scientists have used Big Bang models to guess how much of certain light elements, helium, deuterium, a type of hydrogen, and lithium, exist in the universe compared to normal hydrogen. More exactly, they can predict the amounts of helium-4, helium-3, deuterium, and lithium-7. These amounts depend on one key factor: the number of photons, light particles, compared to baryons, particles like protons and neutrons. This photon-to-baryon ratio can also be worked out by studying the tiny temperature changes in the cosmic microwave background, the faint glow left over from the young universe. According to these numbers, helium-4 should make up about 1/4 of the universe's total hydrogen mass. Deuterium should be about 1,000th of that mass, helium-3 about 1/10,000th, and lithium-7 an extremely tiny part, about 1/1000th of hydrogen's mass. When astronomers measure the real amounts of these elements in space, they mostly agree with what the Big Bang theory predicts. The agreement is especially strong for deuterium. Helium-4 is slightly off from the predictions but still close, while lithium-7 is different by a factor of 2, a puzzle known as the cosmological lithium problem. Some of this difference may come from limits in how well we can measure. Even with these small gaps, the overall match between predictions and what we see is strong proof that the Big Bang really happened. This theory is still the only clear reason why light elements exist in the amounts that they do. In fact, it would have been almost impossible for the Big Bang to have made much more or much less than between 20 and 30% helium. Without the Big Bang, there is no clear reason why the early universe, long before stars formed, should have had more helium than deuterium, or why these elements should be found in fixed amounts across the universe. Scientists have closely studied the shapes and spread of galaxies and quasars, and their results match what the Big Bang theory predicts. By joining real observations with scientific models, they have learned that the first galaxies and quasars started forming within about 1 billion years after the Big Bang. Over time, these cosmic structures have grown into huge clusters of galaxies and even bigger superclusters. As the universe has aged, the stars inside galaxies have changed. When astronomers look at galaxies that are very far away, they are really seeing them as they were billions of years ago in the early universe. These faraway galaxies look quite different from the ones closer to us, which show a more recent stage of cosmic change. Galaxies that formed more recently do not look the same as galaxies that formed at similar distances soon after the Big Bang. This clearly goes against the old steady-state theory, which claimed that the universe was always the same and had no beginning. Scientists have also found that patterns of star birth, the spread of galaxies and quasars, and the structure of the universe all match very well with what Big Bang computer models predict. These finds are helping scientists better understand how the universe took shape. In the year 2011, astronomers made a stunning find. By studying the light from faraway quasars, they saw what seemed to be untouched clouds of the very first gases in the universe. Before this, every object ever seen in space contained heavy elements like carbon, oxygen, and silicon, elements made inside stars. But these two gas clouds had no signs of such elements, which means they likely formed just minutes after the Big Bang, during an event called Big Bang nucleosynthesis. Scientists have also worked out the age of the universe by using different methods. One method measures the rate of the universe's growth with the Hubble constant and the cosmic microwave background. Another method guesses the ages of the oldest stars by studying their life cycles in globular clusters and measuring radioactive elements inside them. More proof comes from studying faraway supernovae and small temperature changes in the cosmic microwave background. All these different tests point to the same age, which strongly supports the main cosmological model known as lambda cold dark matter, or the LCDM model. Still, some results raise questions. One very puzzling object, a quasar called APM 08279 plus 5255, seems so complex that some scientists wonder whether it had enough time to form in the LCDM model. Another major Big Bang guess is that the cosmic microwave background temperature was hotter in the past. Studies of faraway gas clouds support this by showing small absorption patterns in their light. This also suggests that a certain cosmic effect, called the Sunyaev-Zeldovich effect, should stay mostly the same no matter how far away a galaxy cluster is. Scientists have seen this to be roughly true, though it is hard to measure because galaxy clusters themselves change over time. In the future, new gravitational wave observatories may be able to spot ancient gravitational waves, ripples in space-time that could let us see the universe less than 1 second after the Big Bang. If that happens, it could be one of the greatest leaps forward in knowing how our universe began. The Big Bang theory has helped scientists learn how the universe started, but it has also brought many new puzzles. Some of these mysteries have been solved, but others remain. In fact, every time scientists solve one problem, new questions often appear. For example, the horizon problem, the magnetic monopole problem, and the flatness problem are usually explained by the idea of cosmic inflation. But many details about this inflation period are still unclear, and some scientists, even those who first came up with the idea, now think it may not be right. One of the biggest unanswered questions is why there is more matter than antimatter in the universe. According to today's theories, when the universe was extremely young and very hot, it should have had equal amounts of matter and antimatter. But if that were true, matter and antimatter would have destroyed each other, leaving nothing. Instead, the universe we see today is almost fully made of normal matter. To explain this, scientists came up with a process called baryogenesis. For this to work, 3 specific conditions called the Sakharov conditions must be met. These are the number of baryons, particles like protons and neutrons, must not always stay the same. Certain basic symmetries called C-symmetry and CP-symmetry must be broken, and the universe must have moved away from thermal balance at some point. While these things can happen in the standard model of physics, they are not strong enough to fully explain why there is so much more matter than antimatter. Scientists are still looking for a full answer. Findings from exploding stars called Type Ia supernovae have shown that the universe's growth is not slowing down, it is actually speeding up. This was shocking since scientists once thought gravity would slow it down over time. To explain this, they came up with the idea of a strange force, or energy called dark energy. Dark energy is thought to make up most of the universe's energy. Scientists studying the faint glow from the Big Bang, the cosmic microwave background, have found that the universe is almost perfectly flat in shape. According to Einstein's theory of general relativity, this means the total mass and energy of the universe must be very close to a value called the critical density. But when scientists measure the real amount of matter, they find it makes up only about 30% of the critical density. This means the other 70% must come from something else, dark energy. Dark energy also helps explain the overall shape of the universe by affecting huge cosmic structures. It changes how often gravitational lensing happens, when light from faraway objects bends around huge galaxies, and how sound waves move through the young universe, leaving marks called baryon acoustic oscillations. Even though dark energy is the best guess for these effects, its true nature is still unknown. Some scientists think it may be tied to vacuum energy, while others think of more unusual ideas. Data from the Wilkinson Microwave Anisotropy probe in the year 2008 showed that the universe is made of about 73% dark energy, 23% dark matter, 4.6% normal matter, and less than 1% neutrinos. Interestingly, as the universe grows, the share of matter goes down while dark energy stays nearly the same. This means dark energy will keep playing a bigger and bigger role in the far future. Another big mystery is the existence of dark matter, a kind of matter that cannot be seen directly, but has a strong pull of gravity on galaxies. In the 1970s and 1980s, astronomers found that there was not enough visible matter in the universe to explain the gravitational forces keeping galaxies together. This led to the idea that most of the universe's matter must be invisible. Some guesses suggest that up to 90% of all matter in the universe is dark matter. Without dark matter, many things we observe do not make sense. For example, galaxies spin much faster than expected, which means there must be extra unseen mass keeping them together. The large shape of the universe would not have formed in the way we see it today. The amount of an element called deuterium in the universe is far lower than expected if dark matter did not exist. Even though scientists have never directly found dark matter particles, its presence is understood through different observations, such as the way galaxies move inside clusters, the bending of light due to gravitational lensing, the spread of hot gas in galaxy clusters, and the small changes in temperature in the cosmic microwave background. Physicists have suggested many possible types of dark matter, including unusual particles that do not interact with normal matter, except through gravity. Experiments in many places around the world are trying to detect these particles, but none have been found yet. Even though it is the best explanation for many cosmic observations, the dark matter idea is not perfect. There are some problems still not explained, including the dwarf galaxy problem, where computer models predict that there should be far more small galaxies than we actually see, and the cuspy halo problem, where the centers of galaxies should have a sharp rise in dark matter density, but observations show a smoother spread. Some scientists have suggested other ideas that change our understanding of gravity instead of needing dark matter. However, none of these other ideas have been able to explain all observations as well as the dark matter model. One of the biggest challenges in modern physics is the so-called cosmological constant problem, sometimes called the most embarrassing problem in physics. This comes from the fact that the amount of dark energy in the universe, as measured by astronomers, is very different from the value predicted by quantum physics. According to calculations based on basic physics, the energy density of empty space should be much, much larger than what is actually seen. Scientists do not have a clear explanation for why the universe's dark energy is so small compared to these predictions. To solve this, some researchers think that dark energy could be linked to Einstein's cosmological constant, a term he first added and later dropped in his equations. Others suggest more complex ideas, such as quintessence, which says that dark energy changes over time instead of staying the same. Even with all the progress scientists have made in understanding the universe, many mysteries remain. The nature of dark matter and dark energy, the imbalance between matter and antimatter, and the strange speeding up of the universe's growth are all puzzles that astrophysicists are still working on. Each new discovery brings us closer to answers, but it also often opens the way to deeper mysteries. The search to uncover the secrets of the cosmos continues, and the answers may change our understanding of the universe in ways we cannot yet guess. The horizon problem comes from a simple but mind-twisting idea. Nothing, not even information, can move faster than light. Since the universe has only existed for a limited amount of time, this means that only certain parts of space could ever have touched or influenced each other. The line that marks how far any kind of influence could have reached is called the particle horizon. Here is where the problem appears. When we look at the cosmic microwave background, the faint glow left from the early universe, it looks almost the same in every direction. But if the universe had always been filled only with radiation and matter, as scientists once thought, then regions more than about 2 degrees apart in the sky should never have had the chance to share heat or energy. So how did they all end up at the same temperature? The answer to this puzzle comes from a powerful idea called inflation theory. This theory says that at an extremely early time, long before atoms or even basic particles like protons and neutrons existed, the universe was filled with a strange, even energy field. During this time, the universe expanded at an incredibly fast rate, growing unimaginably quickly. Because of this sudden expansion, areas that today seem impossibly far apart were actually close together before inflation started. That means they could have shared heat and balanced their temperatures before being pushed apart by inflation. This explains why the cosmic microwave background looks so smooth and even across the sky. There is another amazing effect of inflation. Quantum fluctuations, tiny random energy blips predicted by Heisenberg's uncertainty principle, were stretched to enormous sizes. These small changes became the seeds of galaxies, stars, and cosmic structures we see today. Inflation predicts that these early changes were almost perfectly balanced, and modern studies of the cosmic microwave background confirm this. While inflation explains a lot, it raises another hard question. According to most models, inflation ended long before the electroweak era, the time when basic forces like electromagnetism and the weak nuclear force split into separate forces. If faraway parts of the universe were already cut off from each other by then, why do we not see big uneven patterns in the universe today? This is still an open question in cosmology. Back in the 1970s, physicists working on grand unified theories predicted the existence of magnetic monopoles, particles that act like single north or south poles of a magnet. These objects should have formed in huge numbers in the early, high-energy universe. But after many decades of searching, no one has found even one. Inflation solves this puzzle in a simple way. It stretched the universe so much that any monopoles that did exist were spread out so widely that they became almost impossible to detect. Another strange feature of the universe is its flatness. Space can be positively curved like a sphere, negatively curved like a saddle, or flat like a sheet of paper. The shape depends on the universe's total energy density. If the density had been even slightly different in the past, the universe would have either collapsed long ago or expanded into a nearly empty void. Yet, after billions of years, it still looks amazingly flat. To make this clear, at the time of nucleosynthesis, when the first atomic nuclei formed, just a few minutes after the Big Bang, the density of the universe had to be within 1 part in 10 quadrillion of the perfect value to stop either a runaway collapse or endless growth. That level of balance is very hard to explain unless something actively pushed the universe toward flatness. Inflation gives the answer again. Just as a balloon being blown up smooths out its surface, the extreme stretching of space during inflation forced the universe toward flatness, making sure we live in a cosmos that still looks balanced today. Many people wrongly believe that the Big Bang theory explains how everything, including time, space, and energy, first came into being. But that is not quite true. The Big Bang theory does not tell us what caused the universe to exist. It explains how the universe we see today grew from an extremely small, very hot, and dense state. A common mistake is thinking of the Big Bang as a small object suddenly expanding, like a balloon being filled with air. But when scientists talk about the size of the universe at the time of the Big Bang, they mean only the part of the universe we can observe. The entire universe may be far larger, or maybe even infinite, and we may never fully know its true size. Another mistake is thinking of the Big Bang as an explosion, where matter was thrown apart like pieces from a bomb. In reality, what happened was the stretching of space itself, like a growing fabric carrying galaxies with it. Some scientists call this the stretching of space, while others call it objects moving apart. Both views can be correct depending on how you look at it. According to Hubble's law, the farther away a galaxy is, the faster it seems to move away from us. Some galaxies even seem to be moving faster than light. But this does not mean they are breaking the laws of physics. Instead, space itself is stretching, making the distances between galaxies grow faster with time. This is not the same as objects moving inside space. Many people have heard that the redshift of faraway galaxies is caused by the stretching of space. While this is partly true, the most straightforward explanation is something called the Doppler effect, the same effect that makes a passing ambulance sound different as it moves toward or away from you. In this case, as light travels across the universe, it gets stretched into longer wavelengths, shifting toward the red part of the spectrum. Scientists can make guesses about what will happen to the universe, but only for a limited stretch of time, although that limit is far longer than the present age of the universe. Beyond that point, things become much less clear. In the same way, while scientists have learned a lot about the universe's first moments, the real beginning of everything is still not known. When the Big Bang first took place, the universe was unimaginably hot and dense. The Belgian scientist Georges Lemaitre called this starting point the primeval atom, while another scientist, George Gamow, used the word ilum to describe the thick material that filled the early universe. We still do not know exactly how or why this first state appeared, but the Big Bang idea does give us some hints about how the universe changed afterward. Scientists have also suggested that our universe is steady because of the way natural laws work. Some ideas even suggest that there could be an endless number of universes, and only those with the right conditions could create life. But what was there before the Big Bang? This is one of the greatest puzzles in physics. The Big Bang idea is built on Einstein's general relativity, but at extremely high heat, this idea no longer works. To truly understand the very first moments of the universe, scientists need an idea that joins gravity and quantum mechanics, something called quantum gravity. Some theories even suggest that time itself may not have existed before the Big Bang, meaning that asking what happened before might not even make sense. Although we do not yet have clear answers, scientists have come up with many interesting ideas about what might have happened before or during the Big Bang, quantum fluctuation model. This idea says that the Big Bang may have been caused by a sudden random change in a quantum field. Even though it seems extremely unlikely, in an endless amount of time, even the rarest events can finally take place. The emergent universe. Some ideas describe the universe as existing forever in a low-energy state before suddenly moving into an expanding state, much like old myths about the universe being born from a cosmic egg. The no-boundary model. Suggested by Stephen Hawking and James Hartley, this idea says that the universe did not have a beginning in the normal sense. Instead of one single point, time and space smoothly appeared from a limited past. Brain cosmology. Based on string theory, this idea says that our universe sits on a giant brain, a higher dimensional surface, and the Big Bang may have been caused by a crash with another brain. Cyclic universe. This idea says that the universe does not have a true beginning or end, but instead grows and shrinks in an endless loop. The Big Bang could have been the result of a past universe falling in on itself, eternal inflation and the multiverse. According to this idea, different parts of the universe may grow at different speeds, forming bubble universes. Our universe could be only one bubble among countless others in a much bigger multiverse. Even though scientists have learned an amazing amount about the Big Bang, many questions are still not answered. Future findings in quantum physics, gravity, and the study of the universe may one day explain what happened in those first unimaginable moments, or even before. Until then, the story of the universe remains one of the greatest puzzles of all time. Before scientists discovered dark energy, they had two main ideas about how the universe might end. The first idea was that if the universe had too much weight, its pull would finally slow its growth and bring everything back together. Over billions of years, the universe would stop growing, shrink, and get hotter and denser until it fell into an incredibly small and fiery state, just like it was at the very start. This idea is called the Big Crunch. The second idea was that if the universe had just the right amount of weight, or even less, it would keep on growing forever, though more and more slowly. Over time, stars would use up all the gas in galaxies, meaning no new stars could be born. The stars that remained would at last burn out, leaving only cold, dead leftovers like white dwarfs, neutron stars and black holes. These leftovers would crash together and join, making bigger black holes. At the same time, the universe would keep cooling, with its heat slowly moving toward absolute zero, a state called the Big Freeze. If protons, the basic parts of atoms, are not steady, then all normal matter would at last break down, leaving only radiation and black holes. Over unimaginable stretches of time, even black holes would fade away as they slowly release energy through Hawking radiation. At this point, the universe would have reached heat death, meaning all useful energy would be gone, and nothing could happen anymore. But newer discoveries show that the universe is not just growing, it is actually growing faster and faster because of a strange force called dark energy. This means that more and more galaxies will finally move so far away from us that we will never be able to see or reach them again. Scientists still do not know exactly how this will end, but one widely accepted idea, called the lambda cold dark matter model, says that galaxies and other groups held together by gravity will stay whole, while everything else grows colder and lonelier, leading to heat death. There is another, more dramatic idea, known as the Big Rip. If dark energy grows stronger with time, it could one day tear apart everything, not just galaxies and stars, but even planets, atoms, and the smallest parts of matter. In this case, the universe would not just fade into stillness, it would be torn apart fully. Beyond science, the Big Bang, the event that began the universe, has stirred deep talks in religion and philosophy. Some people see it as proof of a divine creator, while others think it removes the need for one. This debate has made the Big Bang one of the most interesting meeting points between science and belief. As we try to understand where our universe came from, we run into one of the biggest puzzles in modern science, the singularity. This strange point lies at the very centre of the Big Bang, and scientists believe that everything we see today, space, time, matter, and energy, came from it. But this leads to an even bigger question. What existed before the Big Bang? Imagine a place where the rules of physics stop making sense. A singularity is a point where matter is squeezed into an endlessly tiny space, becoming so dense that gravity becomes unbelievably strong. In this extreme state, space and time twist and collapse in ways we cannot fully understand. Even the most advanced scientific equations, like Einstein's general theory of relativity, fail to describe what happens inside a singularity. This means that, based on what we know now, the laws of physics simply stop working. The singularity that started our universe was even more unbelievable than the ones found in black holes. Instead of being trapped inside a collapsing star, this singularity marked the very beginning of everything. At that moment, all of existence was squeezed into a tiny, unimaginably hot and dense point, a state where no known physical laws applied. Then, in a single instant, this singularity expanded with incredible power, giving birth to space, time, and all the matter that would later form galaxies, stars, and planets. This explosive event is what we now call the Big Bang. Asking what happened before the Big Bang is difficult because it assumes that time already existed. But, according to Einstein's theory of relativity, space and time are woven together into one fabric called space-time. If the Big Bang created space-time itself, then time as we know it did not exist before that moment. In other words, the very idea of before might not even make sense. However, some scientists believe there might be more to the story. Several ideas try to explain what could have come before the Big Bang. Some scientists suggest that the universe did not come from nothing, but instead goes through endless cycles of birth, expansion, and collapse. In this model, the universe expands for billions of years, reaches a peak, then shrinks back into a singularity, before exploding into another Big Bang. If this idea is correct, then something has always existed. Our current universe is just the newest version in a never-ending chain of universes. Quantum physics, the strange science that describes tiny particles, suggests that tiny bits of matter and energy can appear and disappear, even in what seems to be empty space. Some scientists think that the entire universe may have come from one of these random quantum changes. In this view, before the Big Bang, there was a vast emptiness where tiny, unpredictable quantum events took place. At some point, one of these events led to the birth of our universe. Another idea suggests that our universe is just one of many. According to the multiverse theory, an endless number of universes exist, each with its own unique rules. If this is true, then our universe was not the first, and will not be the last. Something has always existed. It just was not necessarily our universe. Before the Big Bang, there may have been another universe, or an entirely different state of reality. In the 1970s, brilliant physicists Stephen Hawking and Roger Penrose made groundbreaking discoveries about singularities. By joining Einstein's general relativity with quantum mechanics, the strange rules that control tiny particles, they gained new knowledge about how singularities work. Their studies showed that singularities are not just ideas on paper, but real points where physics as we know it collapses. They proved that if you rewind time to the very start of the universe, you reach a moment where space bends endlessly and time itself stops working in any normal way. This means that before the Big Bang, there was no familiar space, no ticking clock, no past, just an impossible state of endless density. Science has given us amazing knowledge about how the universe grew after the Big Bang, but the moment before remains one of the greatest mysteries. If time itself began with the Big Bang, then asking what came before might not make sense at all. However, many scientists believe that we simply have not yet found the right laws of physics to explain what happened. In our daily lives, time feels like an unstoppable river, always moving from one moment to the next. We naturally think in terms of before and after, yesterday, last year, even thousands of years ago. But when we try to use this logic to explain the birth of the universe, things become far more complicated. At the heart of this great mystery is the idea of the singularity, a point where all the known rules of physics stop making sense. Some scientists think that time itself began with the Big Bang, meaning there was no before at all. In this view, asking what happened before the Big Bang would be like asking what lies beyond the North Pole. There is simply no direction left to go. This suggests that time, as we know it, only exists inside our universe and did not exist before it was born. But not all scientists agree with this view. Some believe that the singularity may not have been the true beginning, but instead came from something that already existed. One idea suggests that the universe could have come from tiny, random bursts of energy in an empty void, unpredictable changes that somehow sparked the birth of everything. Another idea suggests that our universe is just one in a never-ending cycle, where an older universe collapsed in on itself and then gave birth to a new one. While these ideas are very uncertain and stretch the limits of human understanding, they open the door to exciting possibilities about what might exist beyond what we can see. One of the greatest minds to explore these mysteries was the famous physicist Stephen Hawking. He spent much of his life studying black holes, strange objects in space where gravity is so strong that nothing, not even light, can escape. Interestingly, the center of a black hole has a singularity, much like the one thought to exist at the beginning of the universe. By studying black holes, scientists hope to uncover secrets about the first moments of existence. In one of his most groundbreaking discoveries, Hawking revealed that black holes are not completely dark as people once thought. Instead, they slowly release energy in the form of what is now called Hawking radiation. This discovery was surprising because it meant that black holes can shrink over time and eventually vanish. It also raised an even deeper question. When a black hole fades away, what happens to all the information it once contained? Does it truly disappear, or could there be some hidden way for it to survive? This puzzle challenges our very understanding of the universe. The study of singularities, whether inside black holes or at the birth of the universe, reveals a major problem in modern science. The two most powerful theories we have, Einstein's general theory of relativity, which explains gravity and the movement of large objects like planets and galaxies, and quantum mechanics, which describes the tiny world of atoms and particles, do not work together. At the extreme conditions of a singularity, these two great theories fall apart, leaving scientists searching for a better explanation. Many physicists believe that the missing key is something called quantum gravity, a theory that would combine relativity and quantum mechanics into one complete framework. If such a theory were found, it could help us understand what really happens inside a black hole, what took place during the Big Bang, and whether anything existed before it. For many decades, scientists have worked tirelessly to uncover this missing link. They have created countless ideas and built complex mathematical models, but so far, no one has been able to fully prove how gravity works on the smallest quantum level. This puzzle is crucial because it prevents us from fully understanding one of the most important events in the history of the universe, the singularity at the birth of everything. The singularity is not just the starting point of our universe, it also represents a barrier to our knowledge. It marks the moment when space, time, and matter first appeared, yet it also stands as a wall that science has not yet broken through. In our everyday lives, we understand reality in simple ways. Things have causes and effects, space has 3 dimensions, and time moves forward like an arrow. But the singularity questions all of these ideas. It forces us to think beyond what we can see, measure, or even fully imagine. What if the laws of physics we rely on only began to exist after the Big Bang? What if time itself, as we know it, was not present before that moment? These questions lead us to some of the oldest and deepest puzzles ever considered by humanity. What does it mean to exist? How did something come from nothing? Can we ever truly understand the exact moment when the universe was born? These thoughts have fascinated philosophers, scientists, and thinkers for thousands of years, and they remain at the center of our search for knowledge. As technology improves, we continue pushing the limits of what we know. Powerful telescopes allow us to look deeper into space. Particle colliders help us study the tiniest building blocks of reality, and new ideas try to connect the vast and the tiny into one complete picture. Yet, the singularity remains a mystery, an unsolved puzzle that challenges us to stretch our minds beyond everything we currently understand. It is both an invitation and a challenge, calling us to explore the greatest secrets of the universe and the true nature of reality itself. When we think about the beginnings of the universe, we often picture an empty space before anything existed. But modern science tells a very different story, one that questions our deepest understanding of reality. Instead of a cold, lifeless emptiness, what we once thought of as empty space is actually an unseen, buzzing place filled with energy and strange activity. This leads us into the fascinating world of quantum physics, a part of science that studies how the universe works at the very smallest levels. At the heart of quantum physics is a surprising discovery. Space, even when stripped of all matter and light, is never truly empty. Instead, it is alive with what scientists call quantum fluctuations, tiny, unpredictable flashes of energy that appear and disappear in an instant. These fluctuations are not just random events, they are the base of some of the most amazing discoveries in modern science. They might even hold the answer to one of the greatest mysteries of all. How did the universe begin? For thousands of years, people believed that if you took away everything from a space, every atom, every particle, every bit of light, you would be left with true emptiness. This idea of nothingness was widely accepted by scientists and thinkers alike, but discoveries in quantum physics in the past 100 years have completely overturned this belief. In truth, what looks like empty space is far from empty. Instead, it is a restless sea of energy, always moving and changing because of quantum fluctuations. These fluctuations happen because of something called the uncertainty principle, a key idea in quantum physics introduced by the scientist Werner Heisenberg. This principle says that at the most basic level, we can never know both the exact position and the exact speed of a particle at the same time. This unavoidable uncertainty leads to a strange outcome. Even in what we see as a vacuum, energy constantly flickers in and out of existence. This restless and unpredictable activity creates what scientists call quantum foam, an unseen churning sea of energy at the tiniest levels of reality. Even though we cannot see it with our eyes, its effects can be measured and have been proven through experiments. The first strong evidence that empty space contains energy came in the year 1947. thanks to two Dutch scientists named Hendrik Casimir and Dirk Polder. They carried out a simple but groundbreaking experiment that revealed one of the strangest forces in the universe, now called the Casimir effect. In their experiment, Casimir and Polder placed two small flat metal plates very close together inside a vacuum, a place where, according to classical physics, there should be nothing at all. If space were truly empty, then nothing should have happened. But to their amazement, the plates moved toward each other, as if an unseen force was pulling them together. At first, this seemed impossible. What could be causing this strange pull between the plates? The answer lay in the quantum fluctuations of space itself. Even in a vacuum, energy fluctuations occur all around the plates. However, because the plates were placed so close together, they blocked certain kinds of fluctuations from happening between them. Meanwhile, the space outside the plates still had all possible quantum fluctuations happening freely. This imbalance in quantum energy created pressure, pushing the plates together. This discovery was revolutionary. It showed that what we thought was nothing was actually full of unseen energy. The Casimir effect gave direct experimental proof that quantum fluctuations were real, and that even a vacuum is never truly empty. Now, this is where things become even more amazing. If the empty space of the universe is filled with these tiny bursts of energy, could they have played a role in the birth of the universe itself? Many scientists believe the answer is yes. According to some of the most widely accepted ideas in modern cosmology, the entire universe may have been born from a quantum fluctuation in a very early vacuum. Think of it like this. Instead of the universe emerging from absolute nothingness, it might have come from a state where energy was already present, hidden beneath the surface, waiting for the right moment. Under the right conditions, one of these quantum fluctuations could have suddenly expanded, causing what we now call the Big Bang. This idea is supported by quantum field theory and the theory of cosmic inflation, which suggests that the universe went through an unbelievably fast expansion in its earliest moments. Instead of a universe coming from complete nothingness, it may have burst forth from a quantum vacuum, a place where energy and fluctuations were already bubbling beneath the surface. Even after the Big Bang, quantum fluctuations continued to shape the universe. Right after the universe began, it was unimaginably hot and full of energy. During this time, quantum fluctuations acted like tiny seeds in the fabric of space. At first, these fluctuations were incredibly small, almost impossible to notice. But as the universe expanded, these tiny differences in energy spread out over huge distances. Over billions of years, these tiny variations in energy and density grew under the pull of gravity. Slowly but surely, these fluctuations became the base for galaxies, stars, and planets. Without them, the universe might have stayed perfectly smooth and empty, and life as we know it might never have appeared. The idea of cosmic inflation, first suggested by scientist Alan Guth, explains how these quantum fluctuations were stretched to huge scales in the early universe. This rapid expansion magnified the tiny variations in energy, turning them into the large-scale structures we see in the universe today. The thought that quantum fluctuations could give rise to a whole universe is both exciting and unsettling. If our universe came from a quantum fluctuation, could it be only one of many? Some scientists believe that our universe is just one of countless others that may have formed in the same way. This leads to the idea of the multiverse, which suggests that quantum fluctuations might be constantly creating new universes, each with its own unique rules and laws of physics. In this view, what we see as reality might just be a small part of a much larger cosmic landscape, with universes popping into existence and disappearing all the time. The discovery of quantum fluctuations has broken the old idea of nothingness. It shows that even in the most barren parts of space there is hidden, restless energy at work, energy that may have given birth to the universe itself. Even more surprising is the idea that the universe may not need a traditional cause to exist. In our daily lives, everything happens for a reason. Every effect must have a cause. But in the strange and unpredictable world of quantum physics, things can happen on their own, without any clear reason. Particles can pop in and out of existence. Energy can appear and vanish in an instant. And under the right conditions, a single quantum fluctuation might have created the universe as we know it. This shakes everything we think we know about reality. If the universe could arise from quantum fluctuations, Does that mean reality itself is built on randomness? The idea that our entire universe might have started from an almost invisible ripple in the fabric of quantum energy is both astonishing and mind-expanding. It forces us to face one of the deepest mysteries of all time. How did the universe create itself? Quantum physics, the part of science that studies the tiniest building blocks of reality, gives us a surprising answer. It suggests that what we think of as nothing is not truly empty. Instead, it is an unseen, ever-changing space filled with hidden energy, always shifting in ways we cannot see. Imagine a cosmic stage where invisible forces are always at work, tiny bursts of energy flickering in and out of existence like sparks. These short-lived fluctuations may seem small, but under the right conditions they could act as the first sparks that light the birth of something far greater. Maybe even an entire universe. Scientists have long explored this mind-stretching idea through quantum field theory, a system that tries to explain how these mysterious energy shifts work. But this field of study is still young, and many questions remain unanswered. How exactly could these quantum fluctuations have led to the vast and structured universe we see today? What forces guided the change from chaos to order? The truth is, we're only beginning to uncover these cosmic secrets. Yet, the thought that our universe could have come from an unseen, quantum-driven event changes our whole view of creation. It gives us a bold and unconventional way of looking at things, one where the universe may have been born not from an outside force or divine command, but from the strange and powerful properties of space itself. While much is still unknown, one thing is certain. The more we explore, the more we realize that reality is far stranger, more complex, and more incredible than we ever dreamed. This new way of seeing how the universe began changes everything we once believed about existence. Instead of thinking of creation as a single moment that happened billions of years ago, we now see it as a continuing process, a never-ending cycle of birth and destruction that unfolds in the hidden world of quantum physics. In this mysterious realm, the line between nothing and something is not as simple as we once thought. In fact, what looks like empty space is not empty at all. It is filled with unseen energy, just waiting for the right conditions to bring something new into existence. With this view, the birth of our universe was not a one-time event, but part of an endless rhythm of creation. Imagine an unseen cosmic dance, where the chance for new worlds exists in every single moment. What scientists call the quantum vacuum, often thought of as a vast empty void, is really a restless sea of energy, constantly bubbling with activity. Even the tiniest shifts in energy can spark the birth of whole galaxies, stars, and planets. In the study of the universe, there is an interesting idea called cosmic inflation, also known as cosmological inflation or simply inflation. This idea says that in the very first moments of existence, the universe grew at an unbelievably fast rate, much faster than it does today. Think of a tiny dot suddenly stretching into something millions and millions of times bigger in the blink of an eye. This took place right after the Big Bang, laying the base for everything we see today. After this sudden inflation ended, the universe kept growing, but at a much slower speed. Then something even stranger happened. More than 7,700,000,000 years after the universe was born. About 5,400,000,000 years ago, this growth began to speed up again. Scientists believe this is because of a mysterious force called dark energy, which is still not fully understood. The idea of cosmic inflation was developed between the late 1970s and the early 1980s. Several well-known physicists worked on it, including Alexei Starobinsky from the Landau Institute for Theoretical Physics, Alan Guth from Cornell University, and Andrei Linde from the Lebedev Physical Institute. Their work was so important that in the year 2014, they received the Kavli Prize for starting this theory. But why is inflation important? One of the biggest mysteries in the study of the universe is how the large structures of space, such as galaxies, clusters of galaxies, and vast empty regions called cosmic voids, came to exist. Inflation gives a possible answer. Tiny quantum ripples, which are tiny changes in energy during this period of inflation, were stretched to huge sizes. Over time, these ripples became the seeds from which galaxies and other cosmic structures formed. Physicists also think inflation explains other strange features of the universe, It helps us understand why the universe looks almost the same in every direction, why the cosmic microwave background radiation is spread out so evenly, why the universe looks flat instead of curved, and why scientists have never found unusual particles called magnetic monopoles, which some earlier theories said should exist. Even though the idea of cosmic inflation is widely accepted, scientists still do not know exactly what started it. Some ideas suggest that a special kind of field, called the inflaton field, was responsible. This field might have created a force that made space grow faster than the speed of light for a short time, before slowing down again. Many predictions of inflation have been supported by scientific studies. For example, in the year 1992, the COBE satellite found tiny temperature differences in the cosmic microwave background radiation, just as inflation theory had predicted. Later, the WMAP satellite gave even stronger proof. However, not all scientists agree, and some still question whether inflation really happened. The idea that the universe is growing larger goes back to the early 1930s, when astronomer Edwin Hubble made an important discovery. He found that light coming from faraway galaxies was redshifted, meaning that the galaxies were moving away from us. Even more interesting, the farther away a galaxy was, the faster it was moving. This meant the universe was not fixed. It was stretching and expanding. But even before Hubble's discovery, two scientists, Alexander Friedmann and Georges Lemaître, had already predicted that the universe should be expanding based on Einstein's general theory of relativity. They suggested that a powerful push at the start had sent everything outward, and gravity had never been strong enough to stop it. Cosmic inflation might be the missing piece of this puzzle. According to Friedmann's equations, a special kind of energy with negative pressure could cause a powerful repelling effect, making space expand extremely fast. This kind of energy could have come from a quantum field in a false vacuum state, a state where energy is stuck at a higher level before dropping to a lower stable one. In the year 1979, physicist Alan Guth put forward the idea that this inflationary growth could also explain why certain unusual particles, like magnetic monopoles, have never been found. Inflation would have spread them out so much that they became incredibly rare, solving a major problem in physics at that time. Scientists also realized that inflation solves two other major puzzles: the horizon problem. How is it possible that parts of the universe that are billions of light years apart look so much alike? Inflation says they were once much closer together before expanding quickly. The flatness problem. Why does space seem perfectly flat instead of curved? Inflation explains that the rapid expansion stretched out any curves, making the universe appear flat. Looking up at the night sky, there is a limit to how far we can see, not because something is blocking the view, but because the universe itself is expanding. Just like standing on Earth and seeing the horizon where land meets the sky, the universe has its own horizon, called the Cosmological Horizon. This marks the farthest distance from which light has had time to reach us since the universe began. Beyond this limit, space is stretching so fast that light from those areas will never reach us. The part of the universe we can see is just a small piece of a much larger cosmos. There are regions so far away that no light or signals from them have ever reached Earth. These unseen regions lie beyond our current cosmological horizon, which scientists estimate to be about 46 billion light-years in every direction. In the standard view of the Big Bang, without adding extra ideas, the cosmological horizon grows over time, showing us new areas of space. But here is a puzzling problem. Whenever we see a new area for the first time, it looks almost the same as the rest. Its background radiation, a faint glow left from the Big Bang, has almost the same temperature as everywhere else. Its space-time shape, or the way gravity bends space, also matches the rest of the universe. How is this possible? How did these far-off regions know what temperature and shape to have when they were never connected before? This is where the theory of inflation helps. Inflation says that in the very early universe, space grew at an incredibly fast, nearly unimaginable rate because of a powerful energy field, sometimes called vacuum energy, or a cosmological constant. Unlike normal growth, this process kept the cosmological horizon at a fixed distance. This meant that parts of space were quickly pushed apart, stopping them from staying in contact. But since they all began in the same, small, uniform space, they kept the same temperature and shape even after being stretched across the universe. As inflation slowed and this special energy faded, the universe switched to slower growth. The regions pushed beyond our view slowly came back into sight, looking exactly as they had before, keeping their nearly identical temperatures and shapes. This explains why the universe looks so even in places that were never connected. The theory of inflation makes another interesting prediction. It says the overall shape of the universe should be perfectly flat, meaning the total amount of normal matter, dark matter, and leftover energy in space must add up to a precise value called the critical density. Studies confirm this is true. Inflation also helps scientists predict tiny temperature changes across the sky, caused by small quantum ripples that happen during this fast growth. Many of these predictions have been tested and confirmed, giving strong support to the theory. In a universe that grows faster and faster, objects that start close to each other will slowly drift apart more and more, unless a force like gravity holds them together. From the view of one object, the surrounding space acts like a black hole turned inside out. Anything crossing a certain line, its own event horizon, can never return, and even light from it will never come back. This kind of endlessly growing space is called de Sitter space. For it to exist, there must be a special energy known as the cosmological constant, which stays the same over time and keeps space from slowing down. When space grows at exactly an exponential rate, this vacuum energy makes a type of pressure that perfectly balances its energy level. However, in most inflation models, the growth is not perfectly exponential. It is a little slower, which means the horizon grows slowly over time as the vacuum energy slowly fades. This small difference allows scientists to make careful predictions about how inflation shaped the early universe, many of which match what we see today. When the universe was very young, it went through a sudden period of fast growth called inflation. One of the most important effects of this growth was that it stretched out any differences in temperature or density, making everything more even. In simple terms, inflation smoothed out any bumps, making the universe almost the same in every direction and reducing any natural curves it might have had. At this time, the universe was almost completely controlled by a mysterious force field known as the inflaton field. The only small differences that remained were tiny quantum ripples, minute changes that later helped form galaxies and other structures. Another result of inflation was that it greatly reduced the number of unusual heavy particles, such as magnetic monopoles, rare particles predicted by some physics theories. If the universe had ever been hot enough to create these particles before inflation began, they would have been spread out so much that finding even one today would be extremely unlikely. Scientists call these effects the no-hair rule of inflation, an idea borrowed from black hole science. The simple idea is that, just like black holes eventually lose all unique features except for their mass, charge and spin, the universe after inflation lost almost all signs of its earlier complexity, leaving behind a plain, smooth and nearly empty state. Inflation made the universe grow by a huge amount in a very short time. As space grew, the thickness, density of most forms of energy went down because they became more spread out. For example, the thickness of normal matter, like dust, fell by a factor of 8 when the universe doubled in size. Radiation, such as light, lost energy even faster because in addition to spreading out, its waves also stretched, causing what is known as redshift. When the universe doubled in size, the energy thickness of radiation dropped by a factor of 16. But during inflation, the inflaton field kept almost the same energy level. Meanwhile, everything else, irregularities, curves, unusual particles and even normal particles, had their energy spread out so much that they became unimportant. This left the universe extremely even, flat, and mostly empty by the time inflation ended. Inflation was a time of extreme cooling. The temperature fell by an amazing factor of 100,000. In the first models of inflation, scientists guessed that the temperature dropped from about 10 to the power of 27 Kelvin to about 10 to the power of 22 Kelvin. This freezing stage lasted all through inflation. But once inflation ended, the universe's temperature rose sharply again. This process is called reheating or warming, as the great energy stored in the inflaton field turned into normal particles, like those that make up atoms, and electromagnetic radiation. This marked the start of the universe's radiation-filled age. Even though inflation theory explains many things about the early universe, there are still unknowns. Scientists do not fully know what the inflaton field is made of or exactly how reheating happened. However, some think it happened through a process called parametric resonance, where energy moved in a very fast and highly effective way. Back in the 1970s, scientists found many strange issues with the Big Bang theory. To solve these puzzles, physicist Alan Guth came up with the idea of cosmic inflation in 1979. His research began with a simple question: why don't we see magnetic monopoles, made-up particles that should exist according to some physics ideas? Guth found that if space had a special kind of energy called a false vacuum, it would start an incredibly fast growth, an exponential stretching of space itself. Very quickly, scientists saw that this could explain not just the magnetic monopole problem, but also other deep mysteries of the universe. These mysteries all pointed to one strange fact. For the universe to look the way it does today, it had to start in a very exact, fine balanced state. Inflation gives a way for the universe to naturally reach this state, making a cosmos like ours much more likely under the Big Bang theory. One of the biggest puzzles in the study of the universe is called the horizon problem. This problem asks, why does the universe look so even, with galaxies spread out smoothly and the cosmic background radiation having nearly the same temperature everywhere? To explain this, think of a container of gas. The gas spreads out evenly because the molecules have had time to mix and balance their temperature, but the early universe did not have enough time to mix in this way. In the normal Big Bang model without inflation, parts of space that are very far apart today were always too far apart to connect. They were moving away from each other faster than the speed of light, meaning they could never share heat or information. This makes it hard to explain why they ended up with almost the same temperatures. Scientists had tried other ideas before inflation. Georges Lemaitre and Richard Tolman suggested that the universe might have gone through many cycles of growing and shrinking, giving it time to balance out. But their ideas ran into a problem: entropy buildup. With each cycle, disorder would grow, making their models fail. Another idea came from physicist Charles Misner, who suggested a messy early universe, something called the Mixmaster model, that might have smoothed things out. But later studies showed this would not actually fix the problem. Inflation, however, gives a simple and clear answer. It says that before the universe became the size we see today, it went through a time of very fast growth. This means that parts of space that are now billions of light years apart were once right next to each other. They had time to interact, share heat, and then got stretched far apart. This is why the universe looks so even today. Another puzzle is called the flatness problem. When astronomers study the universe, they see that space is almost perfectly flat, meaning its overall shape follows the kind of geometry taught in school, where parallel lines stay parallel and the angles of a triangle always add up to 180 degrees. This is strange because, over time, the curve of space should have become much more noticeable. The density of matter in the universe is very close to the critical density, the exact amount needed for space to stay flat instead of curving into a ball or a saddle shape. But in a universe without inflation, if we go back in time, this fine balance becomes more and more extreme. At the time of the Big Bang nucleosynthesis, when the first atoms formed, the curve had to be 1 part in 10 quadrillion, that is 16 zeros. Any small change from this balance in the early universe would have led to a universe that either grew too fast, stopping galaxies from forming, or collapsed in on itself. Inflation solves this by stretching space so quickly that any first curve gets smoothed out, just like blowing up a balloon makes its surface look flatter. This explains why space today is so close to perfectly flat. According to a group of physics ideas called Grand Unified Theories, GUTS, the forces of nature, electricity and magnetism, the strong nuclear force and the weak nuclear force, were once joined into one single force in the very early universe. When the universe cooled down, this force broke apart like ice forming from water, but these ideas also predict the making of magnetic monopoles, particles that carry a one-sided magnetic pull, like a magnet that has only a north pole or only a south pole. These should have been made in huge numbers in the early universe. If that were true, they would be everywhere today, and yet we have never found even one. Inflation gives a simple fix. If the universe grew massively right after these particles formed, it would have spread them so far apart that they would be almost impossible to find today, too few to detect. In other words, inflation spread them out of existence, but some scientists, including Martin Rees, have pointed out a funny problem with this idea. He said that critics might argue, it's easy to claim success in solving a problem when the problem itself might never have existed in the first place. Even so, inflation is still the best explanation for why we do not see these unusual particles today. In the early days of general relativity, Albert Einstein added a mathematical term called the cosmological constant. He did this to make the universe appear still and unchanging, as many scientists at the time believed it was. His model described the universe as a three-dimensional sphere filled evenly with matter. But Dutch physicist Willem de Sitter later found a completely different answer, one where the universe was growing fast because of the cosmological constant, but with no matter at all. Scientists later saw that Einstein's model was unstable. If even the smallest disturbance happened, it would either collapse or turn into a fast-growing de Sitter universe. Moving forward to the mid-1960s, a physicist named Ernst Gleiner came up with a bold idea. He suggested that in the early universe, pressure was not behaving the way scientists thought. Instead of pushing outward, the pressure was actually negative and directly linked to energy density. This idea, though mostly ignored at the time, would later become the first hint pointing toward dark energy, the strange force that makes up most of our universe today. By the early 1970s, a problem with the Big Bang theory appeared. The Soviet physicist Yakov Zeldovich saw two major puzzles: the flatness problem, why the universe's overall shape looks nearly perfectly flat instead of curved, and the horizon problem, why far apart regions of the universe look so alike even though they could never have interacted. Up until then, scientists thought the universe's smoothness was just luck. In the Soviet Union, these puzzles led two physicists, Vladimir Belinsky and Isaac Kalatnikov, to study a messy math idea called the BKL Singularity, a possible answer for the disorderly first moments of the universe. Meanwhile, in the United States, physicist Charles Misner worked on the Mixmaster universe, a model that used chaotic motion to try to solve these cosmic puzzles, though only with limited success. Then came the late 1970s, when physicists turned to quantum mechanics to study how the universe might have begun. Sidney Coleman, an American physicist, used a math tool called instantons, developed by Alexander Polyakov and others, to explore how unstable states in quantum fields might suddenly switch to more stable ones. He realized that much like water needs a small ice crystal to start freezing, the universe might have needed a tiny bubble of true vacuum to begin its growth. But Coleman did not fully explore the role of gravity in this process, or its link to the growth of the cosmos. One of the boldest ideas in physics suggests that the universe might have come from nothing, with no space, no time, and no matter. This would have happened because of quantum fluctuations, tiny energy shifts that can suddenly create particles. In the years 1978 and 1979, three physicists, Robert Brute, François Engler and Edgard Gunzig, suggested that our universe might have started as a random fluctuation in empty space, followed by a stage where it grew like a de Sitter universe, before turning into the familiar expanding universe we see today. Their idea was groundbreaking because it suggested the universe had no strict beginning in the usual sense. At the same time, another Soviet scientist, Alexei Starobinsky, suggested that quantum effects could play an important role in the early universe. He said that when space-time is curved strongly enough, quantum physics naturally creates something similar to a cosmological constant, leading to a period of inflation where the universe grew extremely fast. His model not only solved the problems pointed out by Zeldovich, but also made predictions about small changes in the cosmic microwave background, the faint glow left from the Big Bang. Around the year 1978, Zeldovich noticed another big puzzle, the magnetic monopole problem. This was a more exact version of the horizon problem, but it applied specifically to particle physics. It suggested that there should be many unusual one-pole magnets in the universe, but none had ever been found. In the year 1980, physicist Alan Guth realized that rapid inflation in the early universe could explain why we do not see these magnetic monopoles. His idea was that the universe, as it cooled after the Big Bang, got stuck in a high-energy state, similar to how supercooled water can stay liquid even below its freezing point. In time, this unstable state broke apart, setting off a rapid, exponential growth known as inflation. At nearly the same time, another physicist, Demosthenes Kazanas, suggested that inflation could solve the horizon problem, while Katsuhiko Sato proposed that it could also remove exotic structures called domain walls. In the year 1981, Einhorn and Sato built on Guth's idea, showing that it not only explained the absence of magnetic monopoles, but also other cosmic puzzles. However, their models required an extremely precise cosmological constant, and the rapid growth could have made the universe too uneven, creating extreme differences in density. Guth further developed his inflation model, saying that the early universe, as it cooled, was trapped in a state of false vacuum, a condition with high energy, similar to the cosmological constant Einstein once suggested. In time, bubbles of true vacuum formed, spreading quickly at the speed of light and wiping out the false vacuum. However, Guth soon saw a major problem. His model did not explain how the universe became filled with the heat and light we see today. The bubble process alone was not enough to reheat the universe properly. For inflation to fully work, something had to create radiation, and in his first model this could only happen if bubbles collided. But if inflation lasted long enough to solve the first problems, then bubbles would be so far apart that they would not collide often enough. This major problem in early inflation models, called the bubble collision problem, was later solved by Andre Linde and separately by Andreas Albrecht and Paul Steinhardt. They suggested a new version called new inflation, or slow roll inflation, which improved the earlier model by Alan Guth, now called old inflation. In Guth's first idea, inflation involved a sudden tunneling from a false vacuum state, but this led to problems with bubbles colliding in a messy way. The new inflation model worked differently. Instead of sudden tunneling, it said that inflation was driven by a scalar field slowly rolling down an energy slope, like a ball rolling down a hill. As long as the slope was gentle, the universe expanded at an exponential rate. But as the slope became steeper, inflation ended, and a process called reheating began, letting energy turn into matter and radiation, setting the stage for the universe as we know it. Over time, scientists found that new inflation did not create a perfectly smooth universe. Instead, tiny quantum fluctuations appeared in the inflaton field. These small irregularities became the seeds for galaxies, stars, and all cosmic structures we see today. The first calculations of these fluctuations were made by Vyacheslav Mukhanov and G.V. Chibisov, while studying a similar model suggested by Alexei Starobinsky. In the early 1980s, researchers at the Nuffield Workshop on the Very Early Universe, held at Cambridge University, also studied these fluctuations. The event, lasting 3 weeks in the year 1982, brought together leading physicists who reached the same conclusion about quantum fluctuations in inflation. Stephen Hawking, Alexei Starobinsky, Alan Guth with So-Young Pi, and a team of James Bardeen, Paul Steinhardt, and Michael Turner each worked separately to confirm these early fluctuations. Even with these problems, inflation theory was improved and became one of the most accepted explanations for how our universe began. Scientists still test and refine these ideas, using observations to uncover the true start of space and time. The idea of cosmic inflation is now a key part of modern cosmology. It helps explain why the universe looks the way it does, why it seems the same in all directions, and why space looks so flat. This idea also solves puzzles, like why we do not see strange particles such as magnetic monopoles, which theories said should exist. Since Alan Guth first suggested inflation in the late 20th century, scientists have found more and more evidence to support it, with one of the strongest proofs coming from the Planck spacecraft's study of the cosmic microwave background. These observations show that the universe is extremely flat, with a margin of error of only 0.1%. They also show that the universe is almost perfectly even, with tiny changes happening only once in every 100,000 regions. Inflation theory says that galaxies, stars, and other large structures we see today grew from small fluctuations in energy in the early universe. These fluctuations, caused by quantum physics, later grew larger because of gravity. Scientists describe these fluctuations as a nearly scale-free Gaussian random field, meaning they follow a pattern predicted by inflation. This pattern depends on just two key numbers, one that sets the strength of the fluctuations, and another that makes a slight adjustment from a perfectly uniform state. Another important prediction of inflation is the tensor to scalar ratio, which tells how many gravitational waves are present compared to the fluctuations in energy. Simple inflation models suggest this ratio should be close to 1/10. Another key part of inflation theory is that all these early fluctuations should have been balanced with one another, a condition called thermal equilibrium. Observations from several space missions, including Planck and the Wilkinson Microwave Anisotropy Probe, WMAP, as well as galaxy surveys like the Sloan Digital Sky Survey, have confirmed this idea. These studies show that the small irregularities in the cosmic microwave background match the predictions from inflation very closely. Scientists have also measured the spectral index, a number that shows how much the fluctuations differ from a perfect balance. If the universe had a perfect balance, this index would be exactly 1. The simplest inflation models predict a value between 92 hundredths and 98 hundredths, and data from the Planck mission suggests a value of about 97 hundredths. This is seen as strong proof for inflation. Over the years, researchers have built many versions of inflation theory, each with slightly different predictions. Most, however, require very exact adjustments to match observations. Even so, inflation remains valuable because it can predict the starting conditions of the universe with just 2 numbers, the spectral index and the fluctuation strength. These predictions stay true no matter the exact way inflation happened. Sometimes new observations seem to question inflation. For example, early data from the WMAP mission hinted that the fluctuations might not be as even as expected, but later data showed this was likely just a random effect. Another strange finding came from studies of the cosmic microwave background, which showed that some fluctuations lined up with the plane of the solar system, something scientists did not expect. Some researchers suggested this could be a sign of new physics, quantum effects, or even mistakes in analysing the data. Scientists still test inflation theory with better measurements. One big focus is on finding B modes, a pattern in the polarisation of the cosmic microwave background that could give direct proof of gravitational waves from inflation. In March of the year 2014, a team using the BICEP 2 telescope said they had found these B modes, pointing to strong proof for inflation. They estimated a tensor to scalar ratio between 15 hundredths and 27 hundredths. But by June of that year, their confidence in the result dropped, and by January of the year 2015, doubts grew stronger. By the year 2018, new data showed that the actual ratio was at most 6 hundredths, meaning the earlier signal was likely false. Other upcoming tests could check inflation further. The Planck spacecraft might give more hints, but it is not clear if the signals will be strong enough to find. Another hopeful method is looking at 21 centimeter radiation, which comes from neutral hydrogen before the first stars were born. This method could give an even clearer view of the universe's early shape. But there are still problems, such as interference from radio signals on Earth and in space, which could make the measurements hard. When Alan Guth first shared his idea of cosmic inflation, some scientists thought that the inflaton, the field that causes inflation, was really the Higgs field. The Higgs field is what gives mass to basic particles, but later studies suggested that this might not be true. One big problem with this idea is that it does not fully fit with test results from particle physics, especially at the electroweak scale. Because of this, many scientists started searching for other answers. Some turned to grand unified theories, or GUTS, which try to bring together the main forces of nature to find a better model for inflation. One of the biggest problems with inflation theory is something called fine-tuning. This means that for inflation to work, the starting conditions must be very exact. In the new inflation model, a rule called slow roll conditions must be met. These rules require the inflaton field to have a very smooth and gentle slope compared to the huge vacuum energy of the universe. The inflaton particles also need to have a very tiny mass. For inflation to work in this model, the universe must have a special type of scalar field with an extremely flat slope, as well as carefully arranged starting points. Scientists have offered reasons for why this might be so. One possible reason involves scale invariant field theories. In these theories, a property called scale invariance, which means the equations look the same at any size, is broken by very small quantum effects. This could explain why the inflationary field has such a flat slope. But this answer only works if the theory can be studied using a math method called perturbation theory. Physicist André Linde suggested another idea called chaotic inflation. He said that inflation is not something that needs very special conditions. Instead, he argued that inflation could naturally happen in almost any universe that begins in a chaotic high-energy state with a scalar field that has no limit to its energy. In this theory, the inflaton field takes on values greater than 1 Planck unit, the smallest useful unit in physics. This is why these models are often called large field models, while competing models, like new inflation, are called small field models. But this idea has its own problems. According to effective field theory, if the inflaton field reaches such high values, the theory's predictions may no longer work. This is because a process called renormalization, used to stop quantum field theory from giving endless or useless results, could bring in big changes that break inflation. Scientists still have not solved this problem, and some say that small field models, where inflation happens at a much lower energy, give a better answer. While inflation depends a lot on quantum field theory and on an estimate of quantum gravity, it has not yet been fully joined with these theories. Physicist Robert Brandenberger pointed out another fine-tuning problem. The size of the tiny ripples in the universe that later became galaxies and groups of galaxies is directly tied to the energy level at which inflation happened. This energy level is thought to be around 10 quadrillion giga-electron volts, which is about 1,000th of the Planck energy. The issue is that the natural energy level in physics is usually the Planck scale, which is much higher. The fact that inflation happens at a much lower energy is sometimes seen as another fine-tuning issue, known as the hierarchy problem. But this is not often seen as a major flaw because the energy level of inflation matches well with the level where the main forces of nature may come together. Many models suggest that inflation never fully stops in the whole universe. Instead, it goes on forever in at least some parts. This happens because parts of the universe that are inflating grow so quickly that they keep making new inflating regions. If the switch from inflation to a normal, non-inflating state is too slow, then new inflating parts will appear faster than old ones fade away. In such models, most of the universe's space at any moment is still inflating, meaning that inflation never really ends on the larger scale. This leads to an amazing result, an endless and always growing multiverse. The idea of a multiverse has caused strong debate among scientists. Some think it is a natural result of inflation, while others say it weakens the whole theory. Physicist Paul Steinhardt, one of the first minds behind inflation theory, was also the first to suggest the idea of eternal inflation in the early 1980s. He said that once inflation starts, it can last forever. He explained how bubbles of non-inflating space, filled with hot matter and radiation, could form inside the inflating universe. But these bubbles would not grow fast enough to spread everywhere, so inflation would keep going in the empty space around them. Later in the same decade, Alexander Vilenkin showed that eternal inflation is a common feature of many inflation models, meaning it would happen under many different conditions. In new inflation models, the inflaton field is expected to roll down its slope, like a ball rolling down a hill. But because of tiny quantum changes, it can sometimes jump back up, creating new inflating parts. Since these higher energy regions grow much faster than lower energy ones, they usually take over the space of the universe. This means that in any model where the inflaton field has no upper limit, inflation will go on forever. But there is a math problem with this idea. While inflationary space acts like de Sitter space, a model of an expanding universe, it cannot stretch endlessly into the past. There must have been a start. Unlike de Sitter space, an inflating universe would one day shrink into a singularity, a point of endless density. Because of this, scientists still need a strong theory to explain how the universe began. In eternal inflation, the inflating parts of the universe grow very fast, while non-inflating parts do not. This means that the inflating part is always much larger than the parts that have stopped inflating. But inflation does end in some regions, letting galaxies, stars, and planets form. One of the biggest debates in modern physics is how to measure chances in different regions of this possible multiverse. Some scientists say that since inflation keeps going in most of the universe, we should expect it never to end. Others say that if we assume a local observer like us must exist to see the universe, inflation must at some point stop. Some physicists think the puzzle of eternal inflation can be solved by asking how much space existed before inflation began. Others say this puzzle is a basic flaw in inflation theory. Strangely, Paul Steinhardt, who first helped create the idea of eternal inflation, later became one of its strongest critics for this reason. Some scientists have tried to avoid the problem of explaining how the universe began by saying that it never had a beginning at all. Instead, they suggest that the universe has always existed, still exists, and will never stop existing. According to these ideas, the universe is endlessly large and has been spreading out faster and faster forever. Other theories suggest that the universe came from nothing, based on ideas from quantum physics and cosmic inflation. One such idea was suggested by physicist Alexander Vilenkin, while Stephen Hawking and James Hartley offered a different one called the no-boundary idea. Their model says that the universe naturally went through inflation right after it appeared, without needing a clear starting point. Physicist Alan Guth called cosmic inflation the ultimate free lunch. He said that new universes, like our own, are always forming inside a huge, ever-growing cosmic background. In this picture, gravity plays a special role. It bends the usual rules of physics but does not break them. Normally, physics says that energy must be saved and that disorder or entropy must always grow. But Guth's idea says that gravity allows for an exception, making new universes without breaking these main rules. Still, some scientists doubt this. One of them, Don Page, said that inflation may not really solve the problem of the universe's starting point. Instead, he thought it made things harder. He said that for the universe to follow the rules of thermodynamics, it would have needed to begin in a very organized, low-entropy state, a case that is very unlikely. If inflation did happen, it would have raised entropy even more, meaning the universe's first state would have needed to be even more orderly than older Big Bang models suggest. This puzzle led some to ask whether inflation really explains the start of the universe, or just makes the mystery deeper. Later, when Hawking and Page tried to work out how likely it was for inflation to have happened, they got unclear answers. Some scientists say this does not matter, because once inflation begins, it lasts forever. As long as the chance of inflation happening is not exactly zero, it would sooner or later take over the universe. Others, like physicists Andreas Albrecht and Lorenzo Sorbo, said that an inflationary universe was much more likely than one without inflation. They argued that inflation needs much less starting energy to begin compared to a model where inflation never happens, making it the more likely case. Another problem, known as the Trans-Planckian problem, comes from the fact that inflation happened at energy levels not far from the smallest possible scale in physics, the Planck scale. Some scientists say that before inflation, quantum ripples in space were so tiny that they were smaller than the Planck length. If this is true, then unknown laws of quantum gravity might have shaped how the early universe began. The effect of this is still argued about. Some think these effects are too small to notice, while others think they could be important. A version of inflation, called hybrid inflation, builds on an earlier idea known as new inflation. It brings in extra energy fields, where one field controls the universe's growth and another decides when inflation ends. In this model, inflation does not go on forever. Instead, after lasting long enough, one of these fields reaches a point where it suddenly makes inflation stop, letting the universe keep changing in a new phase. This idea of inflation is somewhat like the strange force called dark energy, which is now making the universe grow at a faster and faster rate. But dark energy works at a much lower energy level, about 10 to the power of negative 12 giga-electron volts, which is about 27 steps lower than the energy level where inflation happened. A big step forward came with the finding of flux compactifications, which helped connect inflation to string theory. One form of this idea, called brane inflation, says that inflation happens when special objects in string theory, called d-branes, move through hidden dimensions. These branes meet with anti-d-branes, setting off inflation in a way different from older models. But scientists still do not fully understand how this works. It looks like inflation here happens through a process like old inflation, where the universe shifts from one state to another by quantum tunneling. After that, another process must take over to finish inflation. Another idea comes from a field called loop quantum gravity, which says that space itself is made of tiny separate pieces. In this idea, if the energy of the universe ever grows too high for this chunked space to hold it, the universe could bounce instead of falling in on itself, giving another possible answer for how inflation began. Even though these theories explore different paths, they all try to answer one of the biggest questions in science. How did the universe begin, and what forces shaped its growth? Scientists have suggested different ideas to explain the mysteries of the early universe, and some of these give other options to the widely accepted idea of cosmic inflation. One such idea is the Big Bounce theory, which says that instead of the universe starting from an endlessly small and heavy point, a singularity, it first went through a time of shrinking before suddenly growing again. This bounce gives an answer for the conditions that led to the Big Bang. It naturally solves two big puzzles in space science: the flatness problem, why the universe looks so smooth and even on big scales, and the horizon problem, why different parts of the universe which should never have touched still look the same. This answer comes from a changed version of Einstein's theory of gravity, called the Einstein-Cartan-Siyama-Kibble theory. Unlike normal general relativity, this theory adds an extra factor called torsion, which changes how particles act in extreme states. Put simply, when the universe was very dense, torsion made a force that stopped it from shrinking into an endlessly small point. Instead of a singularity, there was a smallest size before the universe bounced back into growth. This early fast growth explains why the universe now looks flat, smooth, and even on the bigger scales. As time went on and the universe spread out, the effects of torsion faded, leading to the radiation-filled phase we see in early space history. Another group of ideas, called ekpyrotic and cyclic models, give a different answer. These say the universe goes through endless cycles of growth and shrinking. Long before the Big Bang, the universe was already growing, which helps explain the horizon problem. Then, during a shrinking time, the universe collapsed into a big crunch, only to be born again in a hot Big Bang phase. This cycle goes on without end. These ideas are like an older thought from the early 20th century called the oscillating universe, suggested by Richard Chase Tolman. But unlike Tolman's idea, which said the universe had a limited life, modern cyclic models allow for a forever universe with no start or end. One problem for these models is whether they can explain the tiny changes in density in the early universe that later made galaxies. There is also debate about whether the universe can really move from a big crunch to a big bang without breaking known laws of physics. One possible strength of these models is that they avoid the magnetic monopole problem, a problem in physics where certain expected particles have never been found. This only works if the heat at the big crunch stays below a key level, called the grand unified scale, which is needed to make these missing particles. If the cyclic model is right, we would not yet see proof of the universe slowing down, since each cycle is thought to last about 1 trillion years. Another option to inflation comes from string theory, which says that besides the 3 dimensions of space we know, hidden extra dimensions exist. These extra dimensions are thought to be very small and curled up, making them unseen in daily life. This idea appears in supergravity models and other theories that try to join quantum mechanics and gravity. A thought called string gas cosmology, put forward by Robert Brandenberger and Qumran Vafa, tries to explain why only 3 dimensions grew large while the others stayed curled up. Their idea imagines the early universe as a hot gas filled with tiny shaking strings, the basic building blocks of nature in string theory. These strings can wrap around extra dimensions, and for a dimension to grow, the strings wrapped around it must be able to cancel each other out. Their math shows this works best in exactly 3 large space dimensions, which matches what we see today. Scientists are still working to improve this idea, especially to see if it can explain the tiny changes in matter that made galaxies. The first version of the theory did not fully solve some big space problems, but later changes adding the bouncing universe idea have helped fix these issues. Yet another idea questions a basic law of physics, the speed of light. Some researchers say that in the very early universe, light moved much faster than it does now. This is called the variable speed of light, VSL theory. If true, it would mean that different parts of the universe could have shared information and energy more easily, solving the horizon problem without needing inflation. In this idea, as the universe grew, the speed of light slowly fell to the value we see today. These other theories give amazing possibilities for understanding how the universe began. While none have yet taken the place of inflation as the main answer, ongoing research keeps looking into whether any of them might fit the cosmic puzzle better. For as long as people have looked up at the night sky, one big question has always stayed in their minds. Are we really alone? Is Earth the only place in this huge, endless universe where life can exist? Or could there be other worlds, hidden among the stars, where living beings thrive just like us? This puzzle has fascinated thinkers, scientists, and dreamers for thousands of years. It is a question that challenges everything we believe we know about life, space, and the very meaning of existence itself. Now, thanks to very powerful telescopes and important new scientific discoveries, we are closer than ever to finding the truth. The search for life beyond Earth, called the hunt for life in space, is one of the most exciting and important quests in modern science. It takes us far beyond the edges of our own solar system to faraway exoplanets, planets that go around stars many light years away from the Sun. It also makes us look at our own solar system in new ways, searching its hidden places for signs of life. As scientists go deeper into this great puzzle, they are also rethinking what life is and what it truly means to be alive. One of the biggest questions scientists are trying to answer is, what makes a planet able to support life? Earth is full of life in every form imaginable, from the tiniest germs to giant trees and enormous sea animals. But why is our planet so special? What conditions make life possible here, and could those same conditions exist on other planets? A key need for life, at least as we understand it, is liquid water. Every living thing on Earth needs water to survive. It helps break down substances, making it possible for chemical changes to happen. Water also carries food materials, helps keep temperatures steady, and supports the basic parts inside cells. Without water, life as we know it could not exist. But why does Earth have liquid water while other planets do not? The answer lies in Earth's special position in space. Our planet sits in a very special area around the Sun called the habitable zone. This is the perfect distance where temperatures are just right, not too hot and not too cold, so that water can stay liquid. Planets that are too close to their stars, like Venus, are so hot that any water on their surface boils away. Planets that are too far, like Mars, are so cold that water turns to ice. But Earth sits in the perfect spot, allowing lakes, rivers, and oceans to exist, making life possible. However, water alone is not enough. Life also needs a source of energy. On Earth, the main source of energy is the sun. Plants use sunlight to make food through a process called photosynthesis. Then animals eat plants or other animals to get the energy they need to live. The sun's energy powers every part of life, from the smallest plants to the largest predators. But what if life could survive without sunlight? Scientists have found that deep in Earth's oceans, far beyond where sunlight can reach, strange creatures live near underwater vents. These are openings on the ocean floor that release heat and chemicals from below Earth's crust. The creatures living there do not use sunlight at all. Instead, they use the heat and chemicals from these vents to make energy, showing that life can exist in conditions very different from those on Earth's surface. This discovery has completely changed how we think about life in the universe. If life can survive in such extreme places on Earth, could it also exist on faraway planets or moons with similar conditions? Some scientists believe that places like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, could be home to alien life. These icy moons are thought to have huge oceans hidden beneath their frozen shells. If heat from their cores provides energy, just like vents do on Earth, then maybe life could be growing in those dark alien waters. But for life to form and change over time, it needs more than just water and energy. It needs steadiness. A planet or moon must have the right conditions for millions or even billions of years for life to grow. Think of it like planting a tree. If the soil, sunlight, and water keep changing too much, the tree will not survive. In the same way, Earth has stayed steady long enough for life to grow and thrive. But what about other worlds? Could they also offer the right conditions for life to change and evolve? The search for life beyond Earth is not just about finding alien creatures. It is about understanding our place in the universe. If we find even the tiniest germ on another planet, it would change everything. It would prove that life is not unique to Earth, that the universe is full of possibilities, and that somewhere, far beyond the stars, we may not be alone after all. One of the most important gifts Earth gives to all living things is its air layer, called the atmosphere. This invisible cover that surrounds our planet plays several key roles. First, it protects us from harmful rays coming from space, which would otherwise be deadly. Second, it helps keep a steady climate by holding in heat and stopping extreme temperature swings. Third, it acts as a shield against strong solar winds that could strip away our planet's surface. Without this protective cover, Earth would be an icy, empty wasteland constantly hit by deadly radiation, a place where life as we know it could not survive. Now think about what it would take for another planet to support life. For a world to allow living creatures, it would need an air layer that protects against space radiation, a way to control temperature so it does not get too hot or too cold, and a strong magnetic field to push away harmful solar winds. These are the same things that make Earth livable. Without them, any planet would be left open to the harshness of space, making it almost impossible for life to grow. This brings us to an amazing question. How many planets out there have the same life-friendly conditions as Earth? Could there be other worlds where life has started and grown just as it did here? To explore this, scientists turn to an idea known as the Drake equation. This math formula, created by astronomer Frank Drake in the year 1961, is meant to guess how many smart civilizations in our galaxy might be able to talk with us. Instead of giving a direct answer, the formula helps break the problem into smaller parts, each one asking about a different thing that could affect whether alien life exists. The Drake equation asks several key questions. For example, how many stars in our galaxy have planets? Out of those, how many planets have the right conditions for life? Among those, how many might produce intelligent beings? And, of the planets with intelligent life, how many civilizations would grow advanced enough to make technology that lets them send signals across space? Even though the Drake equation does not give a clear answer, it serves as a guide, helping scientists organize their search for alien life. It reminds us that many things must come together for a civilization to exist and be found. But here is the great puzzle. If life is common in the universe, why have we not heard from anyone yet? This question is called the Fermi Paradox. We know that the conditions for life might exist beyond Earth, and yet after years of searching, we have found no signs of other civilizations. Scientists and thinkers around the world continue to wonder about this. Where is everyone? If intelligent beings are out there, why have they not reached out? In the year 1950, physicist Enrico Fermi famously asked, "Where is everybody?" His question was based on a simple but powerful thought. If the universe is so huge and filled with countless stars and planets, and if intelligent life is likely, then why have we not found any alien civilizations? This clash between the high chance of life elsewhere and the total lack of proof is what we now call the Fermi Paradox. The paradox makes us face an uneasy truth. With billions of planets spread across the universe, it seems fair to expect that at least some should host intelligent beings. And yet, despite our best efforts, we have found no messages, no radio signals, and no traces of advanced alien societies. The silence is overwhelming. There are many possible reasons for this, but none are proven. One idea is that intelligent civilizations are very rare, making it almost impossible to find them. Another idea is that while life may be common, very few species ever develop advanced tools. Maybe most civilizations destroy themselves before they reach a stage where they can communicate across space, whether through war, environmental collapse, or other disasters. One of the most important gifts Earth gives to all living things is its air layer, called the atmosphere. This invisible shield that surrounds our planet plays several key roles. First, it protects us from harmful rays coming from space, which would otherwise be deadly. Second, it helps keep the climate steady by trapping heat and stopping extreme changes in temperature. Third, it acts as a wall against strong solar winds that could strip away the planet's surface. Without this shield, Earth would be a frozen, empty wasteland constantly hit by deadly radiation, an environment where life as we know it could not survive. Now think about what it would take for another planet to have life. For a world to support living creatures, it would need an atmosphere that protects against space radiation, a way to control temperature so it doesn't get too hot or too cold, and a strong magnetic field to block harmful solar winds. These are the same things that make Earth livable. Without them, any planet would be left open to harsh space conditions, making it nearly impossible for life to grow. This brings us to a big question. How many planets out there have the same life-friendly conditions as Earth? Could there be other worlds where life has begun and grown just as it did here? To explore this, scientists use something called the Drake equation. This math formula, created by the astronomer Frank Drake in the year 1961, was made to guess how many intelligent groups in our galaxy might be able to talk with us. Instead of giving a direct answer, the equation breaks the problem into smaller parts, each one looking at a different thing that could affect the chance of alien life. The Drake equation asks several simple but big questions. For example, how many stars in our galaxy have planets? Out of those, how many planets have the right conditions for life to start? Among those, how many could give rise to intelligent beings? And, of the planets with intelligent life, how many groups would advance far enough to build technology that lets them send signals across space? Even though the Drake equation doesn't give a clear answer, it works like a map, helping scientists plan their search for alien life. It reminds us that many important factors must come together for a civilization to exist and be found. But here's the mystery. If life is common in the universe, why haven't we heard from anyone yet? This strange question is called the Fermi Paradox. We know that the conditions for life might exist beyond Earth, and yet, even after many years of searching, we have found no signs of other civilizations. Scientists and thinkers around the world still debate this puzzle. Where is everyone? If intelligent beings are out there, why haven't they reached out? In the year 1950, the physicist Enrico Fermi famously asked, "Where is everybody?" His question was based on a simple but powerful thought. If the universe is so huge and filled with countless stars and planets, and if intelligent life is likely, then why haven't we found any alien groups? This clash between the high chance of a life existing elsewhere and the total lack of proof is what we now call the Fermi Paradox. The paradox makes us face an uneasy truth. With billions of planets spread across the universe, it seems reasonable to think that at least some should have intelligent beings. And yet, even with our best efforts, we have found no messages, no radio signals, and no signs of advanced alien societies. The silence is overwhelming. There are many possible answers to this mystery, but none are proven. One idea is that intelligent groups are very rare, making it almost impossible to find them. Another idea is that while life may be common, very few species ever develop advanced technology. Maybe most civilizations destroy themselves before they reach a stage where they can communicate across space, whether through war, environmental collapse, or other disasters. For many years, scientists have been searching for signs of intelligent life beyond Earth. Some believe that these advanced groups might be so incredibly far away that their signals haven't reached us yet. Others suggest that the huge distances between us make it nearly impossible to detect them. Another idea is that these civilizations are purposely avoiding us, maybe for their own safety, for moral reasons, or simply because they do not want to contact a species that is less advanced. Even with these challenges, the search for alien life continues. Scientists remain hopeful that one day we'll find clear proof that we're not alone in the universe. If we were to discover intelligent alien life, it would be one of the most amazing and history-changing moments of all time. It would completely change how we understand the universe and our place in it. Even though we haven't yet found aliens, our journey to find the truth has already led to amazing discoveries about space and even about ourselves. This search for alien life is not limited to one country or a small group of researchers. It is a worldwide effort. Scientists from all over the globe are working together, using some of the most advanced tools available to scan the skies for any signs of alien intelligence. One of the main tools used in this search is the radio telescope. These giant instruments are made to detect very specific signals, called narrowband radio signals. These signals are very exact and focused, making them unlikely to come from natural things like stars or planets. Instead, they could be a sign of an advanced group trying to talk across space. While no confirmed alien signals have been found yet, scientists are not giving up. They continue to make their equipment better, making it more sensitive and able to scan larger parts of the sky, raising the chances of finding something amazing. But the search for alien life isn't just about listening for signals. It also means looking for planets beyond our solar system that might support life. Space missions like Kepler and TESS have helped astronomers find thousands of exoplanets, showing that planets are far more common in the universe than we once thought. In fact, there are likely more planets than stars in our galaxy. Some of these exoplanets are in what scientists call the habitable zone, a region around a star where conditions might be just right for liquid water to exist. Since water is needed for life as we know it, planets in this zone are considered the best candidates for hosting alien life. Every new discovery brings scientists closer to finding a planet with the right conditions for life. But while we search the far corners of the universe, there are also amazing possibilities much closer to home. Some of the best places to look for alien life may not be on distant planets, but on moons right here in our own solar system. Two of the most exciting places for possible alien life are Europa and Enceladus, moons of Jupiter and Saturn. At first glance, these frozen worlds might seem lifeless and unwelcoming. However, beneath their thick layers of ice, scientists believe there are huge oceans of liquid water. These hidden oceans could provide the perfect place for life to exist, even in extreme conditions. Water is one of the most important parts of life, and these underground oceans might have everything needed to support living creatures. Europa, in particular, has caught the interest of scientists for many years. NASA is preparing to launch the Europa Clipper mission soon, which will study the moon closely. This spacecraft will look for signs of life beneath Europa's icy surface by studying its ocean, ice, and other features. Scientists are especially interested to see if the conditions on Europa are like deep-sea areas on Earth, where strange and tough creatures live without sunlight. Enceladus is another exciting choice for hosting life. In the year 2005, NASA's Cassini spacecraft made a groundbreaking discovery. It found that Enceladus was shooting huge plumes of water vapor into space. These plumes suggest that there is a vast liquid ocean beneath the ice, and they might contain the chemicals needed for life. If tiny microorganisms exist in these hidden waters, it would be an amazing breakthrough, proving that life can exist beyond Earth. What makes these icy moons so exciting is that they could help us understand how life might survive in the harshest places. If life can exist in the dark, hidden oceans of Europa or Enceladus, then it's possible that similar conditions exist on other moons or planets across the universe. This could completely change how we think about the search for alien life, leading us to look beyond Earth-like planets and consider totally new possibilities. The search for life beyond Earth is one of the most exciting and deep challenges humanity has ever faced. It makes us question everything we know about life, the universe, and our own existence. Are we truly alone in the cosmos, or is there something, or someone, out there, waiting to be found? Every time we detect a strange signal, find a new planet, or uncover proof of a hidden ocean, we take one step closer to answering that ultimate question. The Anthropic Principle is an idea in the study of the universe that says the universe must have the right conditions for life because, if it did not, no one would be here to see it. In simple terms, the universe looks perfectly set up for life, only because a universe that could not support life would never have thinking beings around to ask about it. People who support the Anthropic Principle believe this idea helps explain why the universe has a certain age and certain unchanging numbers that make life possible. If these numbers were even a little different, intelligent life might never have appeared. For example, if the universe were much younger, there would not have been enough time for stars to make the heavier elements needed for planets and living things. If it were much older, most stars would have burned out, and star systems like ours might not exist. Scientists have long asked why the basic physical numbers, the fixed values that guide physics, are exactly what they are. The Anthropic Principle says they must be this way, because only a universe with these conditions could support life. It is not that the universe was made for life, but that life could only arise in a universe with the right setup. There are many ways to understand the Anthropic Principle. Some thinkers, like the philosopher Nick Bostrom, have listed about 30 different versions of it. Still, they usually fit into two main groups: the weak Anthropic Principle. This says we see a universe fit for life because life only appears in such a universe. The strong Anthropic Principle. This says the universe must, in some way, be shaped to bring about life. The idea came from noticing that the universe's laws and numbers seem perfectly suited for life. It is an argument based on looking back. If the universe could not support life, we would not be here to talk about it. Some people say calling it the Anthropic Principle is misleading. The word comes from the Greek word anthropos, meaning human, but the idea does not say the universe is made just for humans. Instead, it can apply to any form of life, not only humans or carbon-based creatures. It would work just as well for alien life, stars, or even galaxies. The Anthropic Principle has led to debates, mainly because different versions of it have been used to argue different things. Some critics feel that the principle stops deeper scientific study. For example, the weak Anthropic Principle is sometimes seen as unscientific because it cannot be tested or proven false. On the other hand, stronger versions make bold claims that are still argued over because they rely on evidence that is hard to check. In the year 1961, physicist Robert Dicke said that the universe must have a certain age fit for life. If it were 1/10 of its current age, elements like carbon would not have had time to form, and planets like Earth would not exist. If the universe were 10 times older, most stars would already be dead, leaving behind mainly white dwarfs and faint red stars, making it unlikely for star systems to survive. Dicke also said that the universe's matter must be close to a critical density, just enough to stop it from collapsing in a big crunch, but not so much that it would prevent it from expanding. Later studies showed that normal matter makes up about 30% of this critical density, while the rest is probably due to dark energy. In the late 20th century, physicist Steven Weinberg gave an anthropic reason for the strange cosmological constant, a number that controls how fast the universe expands. The predicted value of this constant from particle physics is far off from the one we actually see, by about 120 orders of magnitude. This has been called the worst prediction in physics. But Weinberg pointed out that if the cosmological constant were just a little larger, the universe would have expanded too fast for stars and planets to form, and without them, there would be no life. Some scientists say that the physical numbers controlling the 4 basic forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, seem perfectly balanced to let life exist. If, for example, the strong nuclear force were increased by just 50%, it would change the way elements form in stars, stopping the creation of hydrogen, the key part of water and life as we know it. In the same way, small changes in the other forces would greatly affect the universe's age, shape, and ability to support life. The name Anthropic Principle was first used by Brandon Carter, a physicist, at a 1973 meeting honouring the 500th birthday of Copernicus. Carter brought up the idea as an answer to the Copernican principle, which says humans do not have a special or central place in the universe. Carter suggested that, even though humans are not the centre of the universe, the conditions we see must still be somewhat special because they allow intelligent life to exist. At that time, the steady-state theory, which said the universe always looked the same and had no beginning, was still popular. But this theory was overturned in 1965 with the finding of the cosmic microwave background radiation, clear proof that the universe has changed over time, most likely starting with the Big Bang. In the year 1973, physicist Brandon Carter explained 2 ideas under what he called the Anthropic Principle. The first, called the weak Anthropic Principle, said that humans only exist in certain times and places in the universe because those places happen to be fit for life. The second, more debated idea, the strong Anthropic Principle, went further. It said the basic numbers of physics, the ones that shape the universe, might be set in a way that makes life possible. At first, the weak version seems reasonable. After all, humans could have developed in many different times and places, as long as conditions were right. But the strong version is harder to explain. There is only one known universe with fixed physical laws, so why do those laws allow life at all? Carter gave 2 possible answers. First, humans can make good guesses about the physical numbers of the universe based on the fact that they exist within it. But if that does not seem like enough, there is another answer. Maybe there is not just one universe. Maybe there are many, perhaps an endless number, each with its own physical laws. This idea, now called the Multiverse theory, though Carter first called it the world ensemble, would mean that our universe is only one among countless others, and we happen to live in one that allows life. This idea is daring, even radical, but it may help explain a deep puzzle. Why do the laws of physics seem so perfectly balanced for life? If there are countless universes, most would not allow life, but a few would. Naturally, humans would only exist in one of the just right universes, so it should not surprise us that we live in one. Since Carter's paper, the Anthropic Principle has taken on many different meanings. A big turning point came in the year 1986 when scientists John D. Barrow and Frank Tipler gave new versions of the weak and strong anthropic principles, different from Carter's original ideas, which caused confusion among scientists. But Carter was not the first person to think about such ideas. As early as the year 1904, evolutionary biologist Alfred Russel Wallace suggested that the universe might need to be as huge and complex as it is in order to make a world able to support human life. Then, in the year 1957, physicist Robert Dicke said that the age of the universe is not random. Living conditions decide why we exist at this point in cosmic history. He also said that if the basic numbers of physics were even slightly different, humans would never have existed to ask these questions. Even before these scientists, Austrian physicist Ludwig Boltzmann had thought about similar ideas in the late 19th century. Boltzmann wondered why the universe seemed to have such low entropy, a measure of disorder, when the rules of thermodynamics said it should be much more chaotic. He suggested that random changes could create short-lived pockets of low entropy, small areas where order briefly appears out of chaos. He argued that humans happen to exist in one of these rare, orderly areas, simply because that is the only kind of place where intelligent life could arise. Carter's version of the anthropic principle has led to much debate, partly because it is based on a simple but easy to misunderstand idea. The universe seems finely tuned for life, so maybe it really is. Scientists such as Stephen Hawking and Michael Collins said, this might mean that there is not just one universe, but an endless number of universes, each with different starting conditions. If this is true, then the reason our universe looks so finely balanced is simply that we would not be here to notice it otherwise. Most universes would not allow life, but in an endless multiverse, at least a few would, and ours is one of them. Though scientists have wondered about similar ideas for hundreds of years, by the early 1970s the only scientific theory that allowed for many universes was the many worlds interpretation of quantum physics. This theory says that every quantum event creates branching timelines, but it does not allow for changes in the basic physical constants. Since then, however, new theories have appeared. In the 1980s, the mix of inflation theory and symmetry breaking in the early universe gave a possible way for physical constants to change across different parts of space. By the early 21st century, string theory suggested an even more striking idea. What if every basic constant, including the number of space dimensions, could change across an unimaginably huge landscape of possible universes? This idea is very different from the old goal of scientists, to find one complete theory of everything with no free choices. Albert Einstein once asked whether God had any choice in setting the laws of physics. In other words, was the universe meant to be exactly the way it is, or could it have been different? In the year 2002, some scientists working on string theory believed they were close to removing the need for the anthropic principle. But by the next year, scientist Leonard Susskind argued that the opposite might be true, that the great complexity of the landscape of possible universes actually made the anthropic principle seem more believable than ever. The anthropic principle also plays a part in debates about intelligent design. Believers in intelligent design often point to the fine-tuning of the universe as proof of a creator. Critics, however, say that fine-tuning may not be as amazing as it looks. Some think the universe is not really as finely tuned as people claim, while others suggest that even if it is, this does not clearly prove the existence of a higher power. Some even argue that the anthropic principle itself weakens the case for intelligent design, because it gives another reason for why the universe supports life. Brandon Carter's weak anthropic principle is not something that can be tested through direct observation. It is more of a guiding idea for scientists. The strong anthropic principle, on the other hand, says that the universe is somehow required to support life. Testing this would mean finding proof of life in other universes, but since most meanings of universe say we cannot see others, this creates a big problem. The theory might be impossible to prove or disprove. Thinker John Leslie once made a set of predictions based on the strong anthropic principle, saying that the laws of physics will turn out to be set by chance instead of strict necessity. Theories about many universes will keep gaining scientific support. More proof of fine-tuning in the universe will continue to build up. No forms of life based on non-carbon chemistry will ever be found. Mathematical studies of galaxy formation will show that the universe's expansion rate is crucial for shaping its structure. Some scientists, like Craig Hogan, say it would be very strange if all basic constants were locked in place, since that would leave no way to explain fine-tuning. If that were the case, humans might be forced to accept that the universe simply had to be this way to support life, whether we like it or not. The well-known astronomer Fred Hoyle may have used a special way of thinking called anthropic reasoning to make an amazing guess about the stars. He saw that life on Earth depends on a chemical element called carbon, especially a type known as carbon-12. Since carbon is so important for life, he thought there must be an unknown process inside stars that makes it easier for carbon-12 to form. He studied a particular reaction in stars called the triple alpha process, which creates carbon from smaller helium atoms. Based on this idea, Hoyle guessed that there must be a hidden energy level, or resonance, in carbon-12 that makes this process work well. He even worked out that this energy level should be about 7,600,000 electron volts. Soon after, a research team led by Willie Fowler proved that this energy level really did exist, and their results closely matched Hoyle's guess. But in the year 2010, a historian of science named Helge Krag argued that Hoyle had not really used anthropic reasoning when he made his guess in the year 1953. Krag said that anthropic reasoning, the idea that the universe seems fine-tuned for life, did not become widely talked about until the year 1980. He claimed that Hoyle and other scientists only made the link between carbon and life after the resonance had already been found. Krag called this idea an anthropic myth. Another interesting debate in cosmology is about the theory of cosmic inflation, which explains how the universe grew extremely fast in its earliest moments. A scientist named Don Page criticized this theory by pointing to a big problem. For time to move forward, the universe had to begin with an incredibly low level of disorder, or entropy. But this starting point seems very unlikely, making the whole inflation theory doubtful. However, scientist Paul Davies disagreed. He said that an inflationary version of the Anthropic Principle fixes this problem. Davies agreed that the early universe had to be very orderly, basically a tiny, neat patch of space that later grew into the universe we see now. He believed this actually made the inflation theory stronger, since it removed the need for extra guesses about how the universe began, guesses that other Big Bang theories still need. Another big idea in modern physics comes from string theory, which says that instead of just one universe, there may be a huge number of possible universes. These different universes, called vacua or backgrounds, make up what scientists call the multiverse, or the string landscape. Scientist Leonard Susskind said that if there are countless universes, then anthropic reasoning makes sense, because we only exist in a universe that has the right conditions for life. If other universes do not allow life, we simply never notice them. Famous scientist Steven Weinberg saw the Anthropic Principle as an important shift in scientific thinking. He thought that cosmologists who do not believe in a divine creator could use the principle to explain why the basic constants of nature seem perfectly suited for life. He called it turning point in modern science because it could explain the exact values of these constants without assuming that a higher power carefully adjusted them. But not everyone agreed. Scientists like David Gross, Lubos Motyl, Peter Voigt, and Lee Smolin argued that this way of thinking does not really predict anything useful. Meanwhile, researchers such as Max Tegmark, Mario Livio, and Martin Rees noted that many accepted scientific theories cannot be fully tested yet, but they are still seen as valid. Between the years 2000 and 2002, a scientist named Jürgen Schmidhuber gave another view. He pointed to Ray Solomonoff's theory of universal inductive inference, which gives a logical way to judge scientific theories based on limited observations. Schmidhuber argued that this method already gives scientists the best possible way to decide which theories are most reliable, even if they cannot test everything directly. Two researchers, Jiwei Wang and Samuel L. Braunstein, studied the idea that life's existence in the universe depends on certain basic physical constants. Their results suggested that if scientists do not fully understand these constants, they might wrongly think that the universe was purposely designed for life. This challenges the idea that our universe is uniquely special, because if different constants could also allow life in other universes, then ours may not be as rare as it seems. String theory is a complicated but very interesting idea in physics that says the tiniest building blocks of the universe are not just tiny dots, like traditional particles, but instead tiny vibrating strings. These strings move through space and interact with one another, and the way they vibrate decides the properties of the particles we see, such as their mass and charge. If you look at a string from far away, it acts like a normal particle, but up close, it is really a tiny loop or strand. One of the most important predictions of string theory is that one of these vibrations matches the graviton, a particle believed to carry the force of gravity. Because of this, string theory is seen as a possible explanation for quantum gravity, which tries to join gravity with the strange and powerful rules of quantum mechanics. Scientists are interested in string theory because it offers a possible way to answer some of the deepest mysteries in physics. Over the years, it has helped researchers make progress in understanding black holes, the early universe, and even the forces inside atoms. It has also influenced math research in surprising ways. But the biggest reason string theory is so exciting is that it could be a theory of everything, a single framework that explains all the basic forces of nature, including gravity, electromagnetism, and the nuclear forces that hold atoms together. However, even after many decades of research, scientists are still trying to find out whether string theory truly describes the real universe, or if it allows for too many choices to make clear predictions. String theory first appeared in the late 1960s as an attempt to explain the strong nuclear force, which holds atomic nuclei together. But when another theory, quantum chromodynamics, was found to be a better explanation, scientists set string theory aside. However, they later saw that string theory had surprising features that made it a strong candidate for explaining gravity at the quantum level. The first version of string theory, called bosonic string theory, only included one type of particle known as bosons. Later, the theory grew into what is now called superstring theory, which brought in the idea of supersymmetry. This idea suggests a deep link between bosons and another type of particles known as fermions. Over time, physicists found 5 different versions of superstring theory. But in the mid-1990s, they found strong proof that all 5 were actually different views of one larger theory, called M-theory, which needs a universe with 11 dimensions instead of the usual 3 dimensions of space and 1 of time. In the late 1990s, scientists also found an important connection called the anti-de Sitter conformal field theory, ADS-CFT correspondence. This discovery linked string theory to another major area of physics, quantum field theory, showing that the two could give new insights into each other. One of the biggest problems with string theory is that scientists still do not have a full and clear definition of the whole theory in every case. Another problem is that string theory predicts a huge number of possible universes, making it hard to know which version, if any, matches our own. These troubles have led some physicists to ask whether string theory is truly the right path, or if too much work is being put into an idea that may never be testable. In the 20th century, physicists built 2 major theories that explain the universe. The first was Albert Einstein's general theory of relativity, which describes gravity and the structure of space and time on a large scale, such as planets, stars, and galaxies. The second was quantum mechanics, which explains the strange behavior of tiny particles like electrons and photons. By the late 1970s, these 2 theories were enough to explain almost everything seen in nature, from the smallest particles to the growth of the whole universe. However, despite their success, there was a huge problem. These 2 theories do not work well together. General relativity is based on classical physics, while quantum mechanics follows very different rules. To fully understand the universe, scientists need a quantum theory of gravity, but attempts to join the 2 have faced big problems. String theory is one of the most hopeful ideas for solving this puzzle, but it is still unfinished. String theory starts with an exciting idea. What if the tiny particles we think of as points in space are actually tiny vibrating strings? Instead of treating them as dots with no size, string theory imagines them as very small, one-dimensional threads that move and shake in space. These strings can be either open, like a short line, or closed, forming a tiny loop. The way they vibrate decides their properties, like their mass, charge, and how they interact with other particles. From a distance, these vibrating strings look just like the basic particles physicists already study, fitting into existing models of physics. But when observed on extremely small scales, smaller than anything we can measure right now, they act in a way that could explain mysteries of the universe. One of the most exciting possibilities is that one of these vibrations matches the graviton, a possible particle thought to carry the force of gravity. If true, this would mean that string theory naturally includes gravity, something no other main theory of physics has managed to do. Over the past several decades, physicists working on string theory have made a remarkable finding. Different versions of the theory, which at first seemed separate, are actually connected through mathematical links known as dualities. These dualities show that what looks like one type of theory from one view may actually be another type when seen differently. This finding led to the idea that all consistent versions of string theory might be part of a bigger, united framework known as M-theory. However, no one fully understands what M-theory really is yet. It is still unfinished. String theory has also given surprising insights into black holes and the nature of gravity. For decades, physicists have struggled with strange puzzles that appear when trying to apply quantum mechanics to black holes. In the late 1990s, a breakthrough came with the discovery of the anti-de Sitter conformal field theory correspondence, often called ADS-CFD correspondence. This discovery linked string theory to other well-known areas of physics, helping scientists study black holes in new ways. ADS-CFD has even found uses in areas outside of gravity, such as nuclear physics and condensed matter physics, which study the behavior of particles in extreme conditions. Because string theory tries to include all the basic forces of nature, including gravity, it has been suggested as a possible theory of everything. Many physicists hope that if string theory can be fully worked out, it will give a complete explanation of the universe, including why particles have the masses and charges they do, how dark matter fits in, and even how the early universe grew. However, there are still big problems. Physicists do not yet know whether string theory truly describes our universe, or whether it allows for many different possible universes. One of the biggest problems in string theory is that it is not fully understood in all cases. The easiest way to study how strings behave is through a math method called perturbation theory, which works by making small guesses. However, this method does not show everything about string theory, and physicists do not yet know how to define the theory in its full form without these guesses. Another unsolved puzzle is how string theory sets the vacuum state, the basic state of the universe. Without this knowledge, it is unclear how much freedom the theory has in shaping the universe we see today. Some critics say that these unanswered questions make string theory too uncertain, while others believe it is still worth studying. To see where string theory fits into modern physics, it helps to look at quantum field theory, the base of particle physics. Quantum field theory is the math framework used to describe tiny particles, treating them as ripples in underlying fields. In this theory, scientists work out chances of particle interactions using a method called perturbation theory, which was created in the early 20th century by physicists like Richard Feynman. A key tool in this method is Feynman diagrams, which are drawings that help show how particles interact. String theory builds on these ideas but makes a bold change. Instead of picturing particles as points moving through space, it describes them as tiny strings. In traditional quantum field theory, a Feynman diagram shows a particle's path as a one-dimensional line. In string theory, this line is replaced by a two-dimensional surface, showing the path of a vibrating string. This change alters the math and could explain things quantum field theory struggles with, such as gravity. However, one major problem remains. String theory does not yet have a full definition beyond perturbation theory, making it hard to answer all the questions physicists want to explore. One of the most important parts of string theory is the scale at which it works. The length of a basic string is thought to be about 1/10,000,000th of a trillionth of a trillionth of a meter, the Planck length. This is so incredibly small that, at the scales we can study in experiments, these strings would look like tiny points. Only at the Planck scale do the effects of quantum gravity become important, making string theory a possible explanation for how gravity works at the smallest levels. At first, string theory was developed as bosonic string theory, which focused only on bosons, the particles that carry forces like photons in electromagnetism. However, this version had serious problems, so scientists expanded the idea into superstring theory, which includes both bosons and fermions, the particles that make up matter like electrons and quarks. Superstring theory also uses supersymmetry, an idea that suggests every force-carrying boson has a matching matter particle, fermion, and the other way around. There are 5 main versions of superstring theory: Type 1, Type 2, A, Type 2b, and 2 types of heterotic string theory. Each version allows for different types of strings, and at lower energy levels they produce different physical properties. For example, Type 1 string theory includes both open strings, which have loose ends, and closed strings, which form loops, while the other versions focus only on closed strings. In our daily experience, we know 3 dimensions that describe space: height, width, and length. These 3 dimensions help us understand the shape and size of things around us. However, Albert Einstein's groundbreaking theory of general relativity introduced a shocking idea. Time is not separate from space, but is actually a 4th dimension. Together, they form what scientists call space-time, a 4-dimensional fabric that shapes the very structure of the universe. In this model, gravity is not simply a force pulling objects toward each other, as Isaac Newton once thought. Instead, gravity comes from the way space-time bends and curves around heavy objects like planets and stars. Even though this 4-dimensional space-time model explains a lot about how the universe works, scientists often explore theories that involve even more dimensions. Sometimes, adding extra dimensions makes difficult math problems easier to solve, helping physicists understand the universe better. In fact, certain scientific areas, like condensed matter physics, which studies how materials behave, can be described using theories with just 2 or 3 dimensions. But what if the universe really has more than 4 dimensions, and we just have not seen them yet? Some theories suggest that extra dimensions might exist, hidden in ways we cannot easily notice. One of the most fascinating ideas in modern physics is string theory. This theory suggests that, at the deepest level, everything in the universe is made up of tiny, vibrating strings instead of point-like particles. However, for string theory to make sense mathematically, it needs extra dimensions beyond the 4 we know. Different versions of string theory predict different numbers of dimensions. Bosonic string theory suggests that space-time has 26 dimensions, while superstring theory requires 10 dimensions, and an advanced version called M theory suggests there are 11 dimensions. But if these extra dimensions are real, why don't we see them? One possible answer is in a concept called compactification. This idea says that the extra dimensions are curled up so tightly that they are too small for us to notice. Imagine looking at a garden hose from far away. It might seem like a simple, one-dimensional line. But if you get closer, you will see that it actually has a second dimension, its round width. An ant crawling on the hose would experience both dimensions, but from a distance they seem hidden. In the same way, if extra dimensions exist, they might be curled into shapes so tiny that we do not see them in daily life. To correctly describe the universe using string theory, these extra dimensions must be curled up in a very specific way. Scientists believe they must take the shape of a special 6-dimensional structure called a Calabi-Yau manifold. This structure is named after the mathematicians Eugenio Calabi and Xing-Tung Yau, who studied its properties. Only certain types of Calabi-Yau shapes would allow string theory to properly describe the basic forces of nature, including electromagnetism, the weak and strong nuclear forces, and gravity. Another fascinating way to think about extra dimensions is through something called the brain world idea. In this picture, our entire universe is really a 4-dimensional brain floating inside a higher dimensional space. Think of a soap bubble floating in the air. The surface of the bubble is like our universe, while the air around it represents extra dimensions we cannot directly see. According to this idea, particles and forces like electromagnetism are trapped inside our 4-dimensional universe, but gravity might be able to spread into the extra dimensions. This could explain why gravity is so much weaker than the other basic forces. It might be leaking into hidden dimensions. String theory also brings in the idea of duality, which means that theories that look very different might actually be 2 sides of the same coin. One type of duality, called S-duality, says that a group of particles that strongly interact, frequently colliding and combining, in one theory can be described as weakly interacting, rarely colliding in another theory. This means that complex physical interactions might have simpler explanations from another point of view. For example, Type 1 string theory is mathematically equal to another theory called the SO32 heterotic string theory through S-duality. Another type of duality called T-duality deals with how strings behave in curled-up extra dimensions. It says that if a string moves around a circular dimension of a certain size, it can act exactly like a string moving around a much smaller circle. This means that a universe with large extra dimensions might look the same as one with very small extra dimensions. Type 2a and Type 2b string theories, for instance, are actually equal through T-duality, even though they seem different at first. Duality is a powerful idea that shows up not just in string theory, but in other areas of physics too. A well-known example is the AD-CFT connection, which links string theory to quantum field theory. This surprising link has given new insights into how particles and forces behave at the smallest levels. In simple words, when two theories are related by duality, it means that if you change one theory in a certain way, it will end up looking just like the other. Even though they seem different at first glance, they are really describing the same reality using different types of math. Another important idea in string theory is the idea of branes. A brane, short for membrane, is a multi-dimensional object that stretches the idea of a point particle into higher dimensions. A zero-dimensional brane is just a point, a one-dimensional brane is a string, and higher dimensional branes are called p-branes, where p stands for the number of space dimensions. These branes move through space-time according to the rules of quantum mechanics, and can have features like mass and charge. They also interact with basic fields, just like how charged particles interact with electric and magnetic fields. A special type of brane, called a d-brane, plays an important role in string theory. Open strings, strings with two loose ends, must have their ends attached to a d-brane. The d stands for Dirichlet boundary conditions, a math rule that controls how the strings behave. D-branes have been key in discoveries like the AD-CFT connection, which has helped explain many puzzles in quantum physics. The universe is full of mysteries, and one of the biggest is dark energy. This strange force is what makes the universe expand faster and faster. Scientists think that dark energy makes up about 68% of everything in the universe. In comparison, dark matter, another hidden substance, makes up about 26%, while all the normal matter, the stars, planets, and everything we can see, only adds up to about 5%. Other forms of energy, such as light particles, photons, and neutrinos, are so small in comparison that they hardly count. Even though dark energy has an extremely low heaviness, about 7 times 10 to the power of negative 30 grams in every cubic centimetre, it still controls the universe. This is because, unlike matter, which gathers together into galaxies and stars, dark energy is spread out evenly across space. No matter where you go in the universe, dark energy is always there, filling every part of the cosmos. Scientists first thought dark energy might exist when they studied faraway exploding stars known as Type Ia supernovae. These supernovae act like cosmic measuring sticks because they shine with the same brightness no matter how far away they are. By watching how their light stretches as it travels through space, a process called redshift, scientists can figure out how quickly they are moving away. What they found was shocking. Instead of slowing down, the universe was expanding faster and faster. This was the opposite of what scientists expected. Before this discovery, most believed that gravity from all the matter in the universe would slowly slow down the expansion, much like how a thrown ball slows before falling back to the ground. But the data showed that something, some unknown force, was pushing the universe apart. That force was later called dark energy. There are several ideas about what dark energy could be. One main idea is called the cosmological constant. This says that dark energy is a constant, unchanging force that fills space. It is sometimes described as the energy of empty space, or vacuum energy. Another idea is that dark energy comes from scalar fields, a type of energy that changes over time and space. These fields could act differently in different parts of the universe, making dark energy more changeable. Some versions of this idea include quintessence and moduli fields. Other theories suggest that dark energy could interact with gravity in ways we do not yet understand. One idea, called cosmological coupling, suggests that dark energy and gravity might be linked in some unknown way. Another idea, interacting dark energy, suggests that dark energy might be affected by other unseen forces in the universe. the idea of a strange energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein added something called the cosmological constant lambda into his equations of general relativity. At the time, scientists thought the universe was unmoving, neither expanding nor shrinking. To make his equations fit this view, Einstein added the cosmological constant, which acted as a force pushing against gravity, stopping the universe from collapsing in on itself. But in the year 1929, the astronomer Edwin Hubble discovered that the universe was not still at all, it was actually expanding. This made Einstein see that his first idea was wrong. He later called the cosmological constant his greatest mistake. Ironically, many decades later, scientists found that a repelling force, what we now call dark energy, was indeed pushing the universe apart, meaning Einstein's idea may not have been a mistake after all. In the year 1980, physicists Alan Guth and Alexei Starobinsky suggested a groundbreaking idea called cosmic inflation. This idea says that just after the Big Bang, the universe went through a very short but extremely fast growth, expanding at an unbelievable speed. This inflation period shaped the structure of the universe and explains why galaxies are spread out the way they are today. Inflation looks a lot like dark energy, since both involve very fast expansion of space. But the energy behind inflation was much stronger than the dark energy we see today. Scientists are still trying to understand if these two forces are connected or completely separate. By the 1980s, scientists had built models of the universe that relied heavily on cold dark matter, a form of dark matter that moves slowly compared to the speed of light. These models did a good job explaining how galaxies formed, but they had some problems. For example, they predicted a slower Hubble constant, the rate of the universe's expansion, than what astronomers actually observed. The situation changed in the year 1992 when NASA's COBE spacecraft found small irregularities in the cosmic microwave background, the faint glow left over from the Big Bang. This discovery pushed scientists to rethink their models. A major turning point came in the year 1998, when astronomers studying faraway supernovae found clear proof that the universe's expansion was speeding up, not slowing down. This was the first direct proof that dark energy was real. More discoveries followed. In the early 2000s, experiments like Boomerang and Maxima studied the cosmic microwave background and found that the universe's total energy density was very close to what is known as the critical density, the exact amount needed to make the universe flat on large scales. But when scientists measured the amount of matter in the universe, they found it was only about 30% of this critical density. The missing energy was explained by dark energy. Further proof came from the 2-degree field galaxy redshift survey in the year 2001, which measured the spread of galaxies and showed that dark energy was needed to explain the results. Then, from the year 2003 to the year 2010, NASA's WMAP satellite gave even more exact measurements of the cosmic microwave background, strengthening the Lambda CDM model as the best explanation for how the universe is built and how it changes. The name dark energy was first used in the year 1998 by physicist Michael S. Turner, following the earlier term dark matter, which had been introduced by Fritz Zwicky in the 1930s. Despite all these discoveries, dark energy remains one of the biggest puzzles in modern physics. Some scientists think it could be a basic property of space itself. Others think it might be linked to quantum mechanics, the strange rules that control particles at the tiniest scales. Future experiments, including new space telescopes and large galaxy surveys, aim to find more clues about this strange force. To truly understand how the universe grows and stretches over time, scientists need to take very exact measurements of its expansion. In the world of general relativity, researchers figure out how fast the universe is expanding by studying its shape and a key idea known as the cosmological equation of state. This equation explains how things like temperature, pressure, and the combined amounts of matter, energy, and vacuum energy work together in different parts of space. One of the biggest challenges in modern cosmology is working out the equation of state for dark energy. Scientists believe dark energy plays a major role in the universe's rapid expansion, but its true nature is still a mystery. To study this, researchers include the cosmological constant in the standard model of cosmology, also called the Friedmann-Lemaitre-Robertson-Walker model. This leads to what experts call a lambda cold dark matter model, or lambda CDM model. It is often called the gold standard of cosmology because it closely matches what we actually see in the universe. Since the year 2013, the lambda CDM model has been tested many times through highly exact observations, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from this survey suggested that dark energy acts almost exactly as Einstein's cosmological constant predicts, with an accuracy of about 10%. More recent findings from the Hubble Space Telescope's higher Z team show that dark energy has been affecting the universe for at least 9 billion years, long before the universe began its rapid speeding up. Yet, despite these findings, dark energy remains one of the greatest mysteries in physics. It seems to be very smooth and evenly spread across space, with an incredibly low density. Unlike other forms of energy or matter, it does not seem to interact with anything except gravity. Its density is astonishingly small, about 1 divided by 10 followed by 27 zeros kilograms in every cubic meter, making it almost impossible to detect in laboratory experiments. Yet, even though it is so faint, dark energy makes up about 68% of the universe's total energy. This is because, unlike matter, which clumps together, dark energy spreads out evenly across all of space, deeply affecting the universe's expansion. One main explanation for dark energy connects it to something called vacuum energy. This refers to the tiny changes of particles and antiparticles that constantly appear and disappear in empty space, following Heisenberg's uncertainty principle. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect, meaning it adds to the cosmological constant. This, in turn, is believed to be one of the main reasons the universe's expansion is speeding up. But there is a huge problem. When physicists use quantum field theory to predict how much vacuum energy should exist, they get a number that is far greater than what is actually seen. This massive gap between theory and reality remains one of the greatest unsolved problems in modern physics. Regardless of what dark energy really is, for it to cause the faster spreading of the universe, it must have a very strong pulling force in the opposite direction, called negative pressure. In general relativity, pressure acts in a similar way to mass when it comes to its pull by gravity. Both pressure and mass are part of something called the stress-energy tensor, which decides how matter and energy affect gravity. In the case of dark energy, this opposite pressure works against gravity, making space spread out faster and faster. If the universe was shrinking instead, this same pressure would slow down its squeezing. This effect is sometimes called gravitational pushing away, because it seems to force everything apart, working against the normal pull of gravity. When we break down the universe into its main parts, we see that everything we know fits into 3 wide groups: matter, radiation, and dark energy. Matter includes everything that has mass, from stars and planets to tiny dust grains. As the universe spreads, the energy of matter thins out in proportion to the cube of the spreading factor. Think of a box filled with particles. If the box becomes twice as large, the energy of the particles inside does not just get cut in half, it goes down by a factor of 8 because the space inside grows in 3 directions. Radiation, which includes light and heat, acts a little differently. As space spreads, the energy of radiation drops even faster than that of matter. This is because, apart from spreading over a bigger space, the waves of light and radiation also get stretched. This stretching, called redshift, makes the radiation lose energy quicker than matter does. Dark energy, however, acts in a completely different way. Unlike matter and radiation, its energy does not thin out as the universe grows. Instead, it stays the same, no matter how large the universe becomes. In simple terms, while matter gets thinner as space grows, dark energy remains steady, filling the emptiness evenly and driving the universe's faster spreading. Scientists have gathered many pieces of proof that point to the existence of dark energy, even though it has not been directly found. Distance and redshift measurements. By studying how light from faraway objects has stretched over time, scientists discovered that the universe has been spreading faster in recent times than it did long ago. This shows that something, likely dark energy, is causing this faster growth. The need for extra energy. The universe looks flat in shape. meaning it does not bend inward or outward. For the universe to be flat, there must be a certain amount of total energy. Since normal matter and dark matter together are not enough, scientists believe dark energy must be filling the gap. Patterns in cosmic structures. When astronomers study the large-scale layout of galaxies, they see patterns that hint at the role of dark energy. The way galaxies are spread across space gives more clues about the spreading of the universe and the strange force behind it. In the year 1998, a group of astronomers called the High Z Supernova Search Team made a shocking finding while studying a special kind of exploding star known as Type Ia supernovae. They thought they would find that the universe's spreading was slowing down due to gravity, but instead they found the opposite. It was speeding up. Just 1 year later, in 1999, another group of scientists, the Supernova Cosmology Project, reached the same surprising result. Their groundbreaking work changed our understanding of the universe and earned them the Nobel Prize in Physics in the year 2011. Since then, many more studies have confirmed this finding. Studies of the cosmic microwave background, the faint glow left over from the Big Bang, have given strong proof. Astronomers have also looked at how light bends around huge objects in space, called gravitational lensing, and how galaxies are spread out. All these findings support the idea that a strange force called dark energy is driving the faster growth of the universe. Some doubters argue that the strongest proof comes only from measuring redshift, how light stretches as objects move away, and the distances of supernovae. But other evidence, such as patterns in the cosmic microwave background, also shows that the universe is spreading faster than it would without dark energy. Supernovae are very useful for studying the universe because they act like natural measuring tools, often called standard candles. Scientists know exactly how bright these explosions should be, which helps them tell how far away they are. By comparing a supernova's distance with how much its light has stretched, its redshift, astronomers can measure how quickly the universe is spreading. Type Ia supernovae are especially valuable because they always explode with the same brightness, making them among the most trusted cosmic markers. Recent studies show that dark energy makes up about 71% of the universe, while the other 29% is made of dark matter and normal matter. The leading idea that explains how galaxies, stars, and other cosmic structures form says that matter only makes up about 30% of the universe's total critical density, the amount needed for the universe to stay flat. More proof of dark energy came in the year 2011 from the Wiggles Galaxy Survey, which studied more than 200,000 galaxies. Scientists used a new method to measure distances to galaxies as far as 2,000 million parsecs away. Their results confirmed that the universe has been spreading faster, giving even stronger proof for cosmic speeding up. For the universe to be as flat as it looks, there must be extra energy filling space. All the visible matter, both normal and dark, makes up only about 30% of what is needed. The other 70% is believed to be dark energy. Data from the Wilkinson Microwave Anisotropy Probe, which mapped the early universe, showed that dark energy makes up about 73%. Later findings from the Planck satellite updated this, showing that dark energy makes up about 68%, dark matter about 27%, and normal matter just under 5%. Dark energy also helps explain strange patterns in the cosmic microwave background. When light particles, called photons, travel through regions of strong gravity, like galaxy clusters or empty spaces, they gain or lose energy. This makes temperature changes in the background radiation and is known as the integrated Sachs-Wolf effect. It is seen as another strong clue of dark energy. Scientists are also using a new method to study dark energy by measuring the Hubble constant, which describes how the universe's growth rate changes over time. They study galaxies that have grown in a steady way, treating them like cosmic clocks. By looking at their ages and redshifts, they can estimate how fast the universe was growing at different times. Even with all this proof, dark energy is still one of the biggest unsolved riddles in physics. Scientists agree it plays a key role in making the universe spread faster, but they do not fully know what it is or how it works. To find answers, some are rechecking Einstein's theory of gravity to see if change is needed. Others are studying the exact traits of dark energy, while some are even looking at other possible reasons based on new cosmic findings. One of the simplest ideas about dark energy is that it is a basic feature of space itself. In this view, even totally empty space holds a form of energy, often called vacuum energy. This idea is known as the cosmological constant and is shown by the Greek letter lambda. It is the base of the lambda CDM model, which is now the most accepted idea of the universe's shape. Since Einstein's famous equation shows that energy and mass are linked, this vacuum energy should also have a gravitational effect, changing how the universe grows. But there is a very big problem with this idea. Calculations from quantum physics suggest that the amount of vacuum energy should be unbelievably large, about 120 orders of magnitude higher than what we actually see. If that were true, the universe would have spread so quickly that galaxies, stars, and planets could never have formed. Yet here we are, in a universe where galaxies and stars have formed and changed over billions of years. Something must be cancelling out most of this energy, but not all of it. Scientists do not yet know why, making dark energy one of the greatest puzzles in today's physics. While many believe dark energy is a constant, unchanging force, some scientists think it could be something much more active, an energy field that changes over time. This idea is called quintessence. Unlike the cosmological constant, which stays the same everywhere, quintessence acts like an energy field spread across the universe, affecting its growth in different ways at different times. It is thought to be extremely light so that, unlike normal matter, it does not gather into stars and galaxies. Some versions of this idea suggest the universe's spreading is happening a little slower than the standard model says, but so far there is no strong proof to fully support or reject this idea. One of the biggest unanswered questions about dark energy is why it became the main influence at this particular time in the history of the universe. If it had taken over too early, the universe's fast expansion could have stopped galaxies from forming, and life as we know it might never have existed. Some scientists think this is just a coincidence, while others believe it supports a controversial idea called the Anthropic Principle, the idea that the universe must be the way it is because we are here to see it. Interestingly, some quintessence models include a built-in system, called a tracker, that naturally explains why dark energy became important at this exact time. According to these models, dark energy's behaviour is linked to the amount of radiation in the early universe, which could explain why it appeared later, but with strong effects. Some extreme versions of quintessence predict even stranger situations. One of these is phantom energy, a type of dark energy that gets stronger over time instead of staying the same. If this idea is correct, the universe would not just keep expanding, it could eventually be torn apart in a frightening event called the Big Rip. In this doomsday scenario, the force of expansion would grow so strong that it would first tear apart galaxies, then stars, then planets, and finally even atoms themselves, leaving everything as nothing. Another version of quintessence, called K-essence, suggests that dark energy could be made of unusual forms of energy that act in ways never seen before. Some types of K-essence even suggest the existence of negative kinetic energy, which could have strange and unpredictable effects on the universe's growth. In recent years, astronomers have found differences in measurements of how fast the universe is expanding. This disagreement, called the Hubble tension, suggests that the standard model of cosmology might be missing something important. Some researchers think that only certain types of quintessence models, with extra interactions, can explain this difference. Even though dark energy is still one of the biggest mysteries in modern physics, it is closely linked to Albert Einstein's theory of general relativity. Some scientists say that if general relativity were changed in certain ways, we might not need dark energy at all to explain the universe's faster expansion. Several alternative theories have been suggested, but so far none have been fully proven. In fact, an important discovery, the detection of gravitational waves from the event known as GW 1708-017, has already ruled out many of these changed gravity theories. According to astrophysicist Ethan Siegel, while new ideas about dark energy often make the news, most experts still believe that dark energy is real. Competing theories simply do not match observations as well as the current model. Scientists estimate that the universe's expansion started speeding up about 5 billion years ago. Before that, gravity, mainly from dark matter and normal matter, was slowing everything down. But as the universe grew bigger, dark matter spread out and became less important, while dark energy stayed almost the same. Eventually dark energy took over, causing the expansion to speed up. Every time the universe doubles in size, the amount of dark matter in a given space is cut in half, but dark energy stays almost the same. What happens next depends on the nature of dark energy. If it stays the same, like the cosmological constant suggests, the universe will keep expanding forever. Distant galaxies will move away from us faster and faster, eventually reaching speeds greater than light itself. This does not break any laws of physics, because space itself is stretching rather than the galaxies moving through space. Right now, scientists estimate that the cosmological event horizon, the distance beyond which we can never receive signals or light, is about 16 billion light-years away. If something happens within that distance, its light may still reach us far in the future, but anything beyond that distance will be lost to us forever. As galaxies get closer to this horizon, the light they send out will be stretched into longer and longer wavelengths, eventually becoming invisible. To an observer in the far future, those galaxies will seem to fade away until only our own local group of galaxies is left in an otherwise empty universe. While the idea of an endlessly expanding, dark and empty universe is unsettling, some alternative theories predict more dramatic endings. If dark energy keeps getting stronger, the Big Rip could happen, destroying everything in existence. But there are also theories suggesting that dark energy might change over time, possibly reversing its effects. In that case, the universe could stop expanding and start shrinking in a big crunch, eventually collapsing back into a single point, possibly leading to another Big Bang and the birth of a new universe. Another possibility is that dark energy follows cycles, causing the universe to expand and shrink in an endless loop of Big Bangs and Big Crunches. When we think about the beginning of the universe, the question that often comes to mind is, what was there before anything existed? How did everything come into being from what seems like nothing? This question has puzzled scientists, philosophers and thinkers for hundreds of years, and it touches on one of the deepest mysteries of existence. At the centre of this puzzle is the idea of nothingness, a void, an emptiness, a space that existed long before atoms, stars and galaxies came into being. But the story of this nothingness is far more complicated and fascinating than we might first think. This nothingness is not just an absence of matter, it is a strange state that has the potential to create everything we know. Before diving into the puzzles around nothingness, it's important to understand what we mean by the word nothing. In our daily lives, nothing seems like an easy idea to understand. If you have an empty room, you might think that there is nothing in it. But even then, the room is filled with air, light, and the potential to hold something else. The nothing that space scientists talk about is not this simple emptiness. Instead, it is a state without any matter, energy, or even space itself. It is a true void, a state of complete nothingness. Now, let's imagine a time before the universe was born. There were no stars, no planets, no atoms, and not even the space we think of today. In fact, the very idea of space didn't exist the way we understand it. It was a moment before the Big Bang, a time when the rules of physics as we know them didn't work the same way. At this point, everything we call something was still waiting to be created. So what was this nothingness like? Was it really empty, or was something more subtle and strange happening in the void? According to modern physics, this emptiness was not as inactive as it may seem. In fact, this vacuum of nothingness may have been the birthplace of all the matter, energy, and forces that make up our universe today. The question of how something can come from nothing is often called a paradox. If there was nothing, how could anything come into existence? It seems to go against all logic and common sense. But modern science, especially quantum physics, gives a surprising answer. In the world of quantum physics, nothing is not really empty. Even in a vacuum, there is strange and mysterious activity happening. This activity is called quantum fluctuations. Quantum fluctuations are tiny, unpredictable changes in the energy of empty space. These fluctuations are brief bursts of energy that can appear out of nothing for a moment and then disappear. While these energy bursts are extremely small and short-lived, they are real and measurable. They show that even in a true vacuum, where no particles exist, there is still a kind of activity happening on the smallest levels. We cannot see this with our eyes, but it can be detected and understood through quantum physics. Now, let's bring this back to the creation of the universe. The Big Bang, which is thought to have happened about 13,800,000,000 years ago, was not an explosion in space. It was the expansion of space itself. At the very beginning, all the energy and matter that would eventually form the universe were concentrated in an extremely hot, dense point called a singularity. But how did this singularity come to be? And how did it come from nothing? Some scientists suggest that the energy changes in the quantum vacuum could have started the Big Bang. Basically, the vacuum of nothingness decided to shake things up and create particles, energy, and eventually the entire universe. This process is called quantum creation. It shows that space itself can fluctuate, and under the right conditions, these fluctuations could produce matter and energy. In this way, the rules of physics that control the behavior of particles and energy in our universe could have come from the very nothingness that existed before. This idea leads to a fascinating possibility. Maybe the whole universe, everything we see around us from the smallest particles to the largest galaxies, was born from a quantum fluctuation in the vacuum of nothingness. In this view, the creation of the universe was not a single event, but the result of ongoing fluctuations in the fabric of space and time. So, if the universe came from nothing, how do the rules of physics fit in? How can the universe follow consistent rules if it was created from a void, from a state where no rules existed? This question challenges our understanding of the universe, but it is here that the beauty of science becomes clear. One important idea to understand is that the rules of physics themselves are not random. They come from the basic properties of the universe. When we talk about the rules of physics, we mean the principles that control how matter and energy behave. These rules include gravity, the way subatomic particles interact, and the principles of heat and energy. But where did these rules come from? How did they come out of nothingness? According to current scientific ideas, the rules of physics might not have been the same as they are today, at the time of the Big Bang. In the very early moments of the universe shortly after the Big Bang, the rules of physics may have been very different. For example, it is thought that the universe went through a period of very fast expansion called inflation. During this time, space itself grew enormously, and the main forces of the universe, gravity, electricity and magnetism, and the strong and weak nuclear forces, may not have been separate. In the very high-energy environment of the early universe, these forces might have been combined into a single superforce, which slowly split apart as the universe cooled. The idea that the rules of physics could change over time is amazing, but it is supported by observations and mathematical models made by scientists. As the universe cooled and expanded, conditions changed, and the forces that control matter began to take their present form. It is as if the universe started with very simple general rules that slowly became the complex set of rules we see today. In this way, the universe could have grown from the simplest beginning, a quantum fluctuation in the vacuum, into the highly structured and orderly system that we observe. The rules of physics that we follow today were not imposed from outside the universe. Instead, they are built into the very fabric of space and time, coming naturally from the conditions that appeared after the Big Bang. The quantum vacuum, often called empty space, is not as empty as it seems. It is actually full of potential. At the most basic level, space is filled with quantum fields that stretch across the entire universe. These fields are the building blocks of matter and energy, and they are responsible for creating particles, spreading forces, and even for the existence of space and time itself. Even when there is no matter or energy, these quantum fields are still active. They interact with each other, fluctuating with energy, even without any visible particles. This activity is what causes the strange effects of quantum mechanics, such as particle-antiparticle pairs that appear and vanish instantly. The idea of a quantum vacuum also challenges our usual understanding of empty space. In regular physics, empty space was thought to be a void, a total absence of anything. But in the quantum world, empty space is far from empty. It is a lively, always changing field of energy and possibility. In a way, the quantum vacuum is the source of all creation. It holds the potential for all the particles, forces and structures that make up our universe. The vacuum is not just a quiet emptiness. It is a place where creation can begin, where anything could possibly come from the changes in energy and the interactions of quantum fields. In astronomy, dark matter is a strange and invisible type of matter that we cannot see because it does not interact with light or any other kind of radiation. We know it is there because of the unusual effect it has on gravity, which cannot be fully explained by the known laws of physics unless there is more matter than we can actually see. These strange effects show up when we look at things like how galaxies form and change over time, how light bends around very large objects, called gravitational lensing, and even the way galaxies move within groups. We also notice its effect in the structure of the universe and in the leftover radiation from the Big Bang, called the cosmic microwave background. In the most widely accepted model of the universe, called the Lambda CDM model, the total mass and energy of the universe is made up of 5% normal matter, the kind we see around us, 26.8% dark matter, and 68.2% dark energy. This means dark matter makes up about 85% of the total mass, while dark matter and dark energy together make up about 95% of the universe's total energy. We do not know exactly what dark matter is, but it does not seem to interact with normal matter or light, except through gravity, which makes it almost impossible to detect with current technology. The main idea is that dark matter might be made of tiny unknown particles, like weakly interacting massive particles, WIMPs or Axions. Another possibility is that dark matter could be made of ancient black holes from the early universe. Dark matter can be grouped in different ways depending on how fast its particles move, cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly, which lets them gather together and form structures over time. While most astrophysicists believe dark matter exists, some still question the idea. A small group of scientists, puzzled by certain observations that normal dark matter cannot fully explain, suggest that maybe the laws of gravity need to be changed. They have proposed alternative ideas, like modified Newtonian dynamics or new types of gravity, but none of these ideas can perfectly explain all the evidence we have found so far. This suggests that, even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and fascinating history, full of interesting discoveries and ideas that helped build our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made some interesting observations. He talked about the possible number of stars around our Sun in a book based on a lecture series he gave in Baltimore. Kelvin was trying to estimate how many stars were near the Sun. He did this by studying how stars moved around our solar system. Using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would seem to move in ways that were hard to explain, and this idea led to further thinking about invisible matter in space. Lord Kelvin also estimated the Sun's age to be between 20 and 100 million years, which was later shown to be wrong, but his curiosity about stars and how they moved helped start early ideas about dark matter. A couple of decades later, in 1906, the French mathematician and physicist Henri Poincaré introduced the term dark matter, or matière obscure, while talking about Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, but he also thought that this hidden matter would be less than the visible matter we can see. Although his ideas were far from correct, Poincaré's mention of dark matter brought the idea into scientific discussion. In the 1920s, dark matter continued to interest astronomers. In 1922, Dutch astronomer Jacobus Kapteyn became one of the first to use the speeds of stars to suggest that dark matter might exist. He noticed that the way stars moved in space could be affected by unseen forces, hinting at the presence of invisible matter. Then, in 1930, Swedish astronomer Knut Lundmark expanded on the idea, realizing that the universe must have much more mass than we could observe with our telescopes. This discovery was important because it showed that the visible universe might not be the full picture. In 1932, another Dutch scientist, Jan Oort, joined the discussion by suggesting that dark matter might exist near our galaxy. Oort studied the movements of stars close to our galaxy and concluded that there must be more mass in the galaxy than what we could see. However, he later realized that his measurements were not completely accurate, and more research was needed to understand the true nature of this unseen mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a major breakthrough while studying groups of galaxies at the California Institute of Technology. Zwicky was studying the Coma cluster, a large group of galaxies, and noticed something unusual. The galaxies in the cluster were moving much faster than expected based on the visible mass. This led him to suggest the presence of a huge amount of invisible mass, which he called Dunkel Materie, or dark matter. Zwicky estimated that the Coma cluster had around 400 times more mass than could be seen through telescopes, based on how the galaxies were moving. He thought this unseen mass was responsible for the gravitational force that kept the galaxies in the cluster together. Although Zwicky's estimates were wrong by a large amount, mainly because of outdated values, he was one of the first to correctly identify that the universe must contain unseen mass that pulls things with gravity. Zwicky, however, had a different idea about dark matter than we do today. He thought that dark matter was just ordinary matter that didn't give off light, rather than something completely different, like the mysterious dark matter we think of today. Still, his work was an important step toward discovering dark matter. Over time, more evidence for the existence of dark matter began to appear. One key piece of this evidence came from studying how galaxies rotate. In 1939, H.W. Babcock studied the rotation of the Andromeda Galaxy, which is the closest spiral galaxy to us. He found that the stars on the outer edges of the galaxy were moving much faster than expected. This suggested that there was much more mass in the galaxy than could be seen by just looking at its visible stars. At first, Babcock thought that the strange rotation could be caused by light being absorbed inside the galaxy, or that the outer parts of the galaxy worked differently. But his observations were an early clue that something invisible was affecting the galaxy's rotation. The next year, in 1940, Jan Oort made another important discovery. He studied a galaxy called NGC 3115 and found a large invisible halo of mass around it. This was another sign that galaxies might contain hidden matter, beyond what we could see with the tools we had at the time. The idea of dark matter really began to catch on in the 1970s. Different scientific discoveries came together to suggest that galaxies might be surrounded by huge, invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostriker, Jim Peebles, and Amos Yehiel, and another from Tartu, Estonia, led by Janai Nasto, Ian Saar, and Ants Kasik, came to the same conclusion independently, making the idea stronger. One important observation that pointed to the existence of these invisible galactic halos was the way galaxies rotate. Both optical and radio astronomy played a big role in these findings. Vera Rubin and Kent Ford, using a new spectrograph, made more accurate measurements of the speeds of edge-on spiral galaxies, showing surprising results in the rotation curves. At the same time, radio astronomers used advanced radio telescopes to study the 21-centimeter line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the central parts of galaxies, hydrogen gas extends much farther out. This allowed astronomers to observe rotation patterns at much greater distances, giving them a better picture of the total mass in a galaxy. Early studies of the Andromeda Galaxy, using large telescopes like the 300-foot Greenbank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen rotation curve didn't behave as expected based on Kepler's laws, which describe how objects should move around a center of gravity. As technology improved, more sensitive equipment allowed for even further measurements. In 1975, Roberts and Whitehurst pushed the limits, measuring the rotation speed of Andromeda all the way out to 30 kiloparsecs. Their findings showed that the galaxy's rotation curve stayed flat even at great distances. This was important because it suggested there was much more mass out there, beyond what we could see with regular telescopes. Their charts combined optical data with the new hydrogen data, clearly showing the surprising flatness of the outer galaxy rotation curve. The solid curve in the graph represented the optical data from stars, while the other curve showed the total mass, which kept increasing even in the galaxy's outermost regions. At the same time, scientists were developing even more advanced ways to study galaxies. Using interferometric arrays, multiple radio telescopes working together, researchers like Rogstad and Shostak in 1972 mapped the hydrogen rotation curves of 5 spiral galaxies. They found that all of these galaxies had flat rotation curves as well, suggesting that the mass in the outer parts of the galaxies was much higher than what could be explained by visible stars and light. By the late 1970s, it was widely accepted that dark matter halos likely existed around galaxies, and this became one of the biggest mysteries in astronomy. In the 1980s and 1990s, many observations began to suggest that dark matter was real. One important study done by Persic, Salucci and Stell in 1996 looked closely at 967 spiral galaxies and found strong evidence of dark matter's existence. Other supporting evidence included strange behaviours like gravitational lensing, where galaxy groups bend light from objects behind them, the spread of hot gas in galaxies and groups, and the tiny temperature differences, called anisotropies, in the cosmic microwave background, which is the afterglow of the Big Bang. Today, most scientists agree that dark matter is made of particles that we haven't discovered yet, and these particles are unlike anything we know. The search to find this mysterious particle has become one of the biggest quests in particle physics, with many researchers using different methods and experiments to try to find the truth. In simple terms, when scientists talk about matter in the universe, they mean anything that adds to the overall energy, and its density changes in a certain way as the universe expands. Specifically, it decreases as the cube of the expansion, meaning the further the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows, following the inverse fourth power of the expansion. On the other hand, the cosmological constant acts differently. It stays the same no matter how much the universe stretches, meaning its energy density remains constant. This difference in how matter, radiation, and the cosmological constant act is due to a phenomenon called radiation redshift. When the universe expands, if the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation, the afterglow from the Big Bang, gets weaker because each photon, light particle, has to stretch out over a larger area, reducing its energy. The same happens to ultrafast particles like early neutrinos. They lose energy in a similar way. However, the cosmological constant, being a property of space itself, doesn't change no matter how much the universe grows. As for dark matter, this term usually refers to parts of the universe that we cannot see, yet still have mass and follow similar rules to regular matter. More specifically, dark matter often means a particular kind of invisible matter that isn't made up of the usual particles we know, excluding something called missing baryons. Depending on the situation, the meaning of dark matter can change. The arms of spiral galaxies rotate around their centre, and as you move outward from the centre, the visible mass of the galaxy becomes lower. If all the galaxy's mass were visible, it would behave like a simple system where most of the mass is at the centre and objects orbit it, like planets orbit the Sun in our solar system. Based on Kepler's third law, we would expect the speeds of the objects to slow down the farther they are from the centre, just like planets move slower the farther they are from the Sun. But that's not what we see in galaxies. Instead, the rotation speeds of stars and gas stay the same, or even increase the farther out they are from the centre. To explain this strange observation, it seems clear that the mass distribution in spiral galaxies is different from the solar system. Specifically, there may be a large amount of invisible, non-light-giving matter, what we call dark matter, on the edges of the galaxy. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem to figure out how mass is spread out. However, in many cases, the measured speeds don't match what we'd expect based on the amount of visible mass, even when we consider complex star orbits. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there's more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter because we can measure their mass in 3 different ways. By looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays from the hot gas inside the cluster, and by analysing these X-rays to figure out the temperature and density of the gas. Using the balance between gravity and pressure, we can calculate the total mass of the cluster through gravitational lensing, where the mass of a group bends light from objects that are farther away. This allows us to measure the group's mass without needing to directly watch the movement of the galaxies. All three of these methods point to the same conclusion. Dark matter makes up about 5 times the mass of all the visible matter in these groups. One interesting result of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This happens when large objects like galaxies or groups of galaxies sit between a light source and the observer. These large objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The important thing to know is that gravitational lensing only needs the presence of mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, think of a group of galaxies lying between a very far away object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the dramatic way the light from background galaxies can be bent into arc shapes as it passes through a large object's gravitational field. This has been seen around many faraway galaxy groups, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy group causing the bending. In the weak lensing case, the bending is much less noticeable, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these small changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and normal matter are types of matter, they behave very differently. Early in the universe, normal matter was charged and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also affects the movement and density of normal matter. Because of these differences, normal matter and dark matter evolve in separate ways, and leave clear signs on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, even temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda-CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang, when small irregularities in the universe's density caused matter to collapse and form stars, galaxies, and groups of galaxies. Before this period, the universe was uniform, with no significant differences in density, as described by the Friedmann solutions to general relativity. Over time, tiny differences in density started to grow and clump together, turning the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented normal matter's density differences from growing and forming structures. If the universe only had normal matter, these differences would not have had enough time to evolve into the galaxies and groups we see today. The key to solving this problem is dark matter, which is not affected by radiation. This allowed its density changes to grow first, creating gravity wells that later helped normal matter collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet, pulling in normal matter and speeding up the formation of these large cosmic structures. A striking example of the impact of dark matter is the Bullet cluster, formed by the collision of 2 large galaxy clusters. What makes the Bullet cluster particularly interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This difference is hard to explain with alternative gravity theories, which expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two separate lensing peaks, as seen. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has shown that the universe is expanding faster and faster, a phenomenon usually explained by dark energy. Baryon acoustic oscillations, BAO, refer to regular changes in the density of normal matter, baryons in the universe, which occurred on large scales in the early universe. These changes were caused by sound waves travelling through the hot, dense mix of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB radiation. As the universe expanded, dark matter and normal matter began to clump together, but the effect of the original changes weakened over time. However, we can still see a slight preference for galaxies to be separated by about 147 million light-years, which is a small but measurable sign of these early changes. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current main theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller effect from the galaxy's own motion, called its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look flattened along the line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can see this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987, and was later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what we expect from the lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and improve cosmological models, with results that match findings from the WMAP data. Dark matter is often divided into three types: cold, warm, and hot. These names don't refer to temperature, but instead describe how fast the particles were moving in the early universe. In simple terms, they show how far the particles travelled because of random movements before the universe started expanding and slowing them down. This distance is called the free streaming length, FSL. The type of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's called cold dark matter. If it's about the same size, it's warm dark matter, and if the FSL is much larger, it's hot dark matter. Some theories suggest a mix of these types, which were more popular in the middle of the 1990s, but became less favoured after the discovery of dark energy. The main idea behind the free streaming length is that, after the Big Bang, the universe started with small differences in density, caused by tiny quantum changes at the smallest levels. As these particles moved from denser areas to less dense ones, the fast expansion of the universe limited how far they could go. Faster particles, like those in hot dark matter, could travel further before the universe expanded too much, while slower particles such as those in cold dark matter couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the formation of the large structures, like superclusters, which would later break apart into galaxies. On the other hand, cold dark matter allows for smaller structures, like galaxies, to form first. Recent observations, especially deep field images of the universe, show that galaxies formed first, followed by clusters and superclusters as galaxies grouped together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot make up most of dark matter. Since dark matter refers to any type of matter that interacts with visible matter, like stars and planets, mainly through gravity, it means that dark matter might not be made of a completely new type of particle, but could, in theory, include normal matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, fall into this category. For example, when a black hole pulls in matter, it doesn't treat regular matter, like protons, differently from other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as MACHOs, massive compact halo objects. Some scientists once thought that MACHOs made up most of dark matter, but this idea has since been mostly rejected. There is strong evidence that most dark matter is not made of normal, visible matter. First, if there were enough normal matter like gas or dust scattered around, we would see it when it's lit up by the light from stars. However, we don't see this kind of matter in the amounts we would expect. Next, the Big Bang theory helps us understand how the elements we see today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen more elements like helium, lithium, and other heavier elements. Based on what we observe, only about 4 to 5% of the universe's total mass is made of this normal matter. However, large studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further studies show that only a small portion of dark matter seems to be in the form of normal, hidden objects, like small planets or black holes, called MACHOs. Studies using the bending of light by gravity, gravitational microlensing, suggest that these objects can't make up most of dark matter, as their masses fall in a range that rules out almost all possible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, show that about 5/6 of the matter in the universe doesn't interact much with light or normal matter, except through gravity. This suggests that dark matter is mostly invisible and can only be detected by its gravitational effects. If normal matter, called baryonic matter, doesn't make up most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new, mysterious particles and ancient black holes from the early universe. Unlike normal matter, these non-regular particles don't help create the elements that formed during the Big Bang, a process called Big Bang nucleosynthesis. Instead, we notice them only because of the gravitational effects they cause, such as bending light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with normal particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs, such as gamma rays and neutrinos, which scientists could possibly observe, indirect detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as basic particles that interact through gravity, and possibly other weak forces, like the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to normal particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way, which fits with what would happen if they had masses around 100 billion electron volts and interacted through the electroweak force. This idea is often called the WIMP miracle, because it fits well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a main candidate for dark matter. Researchers are working hard to find WIMPs by looking for the results of their destruction, like gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to make WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results made the simplest WIMP ideas less likely. Axions, another candidate for dark matter, are theoretical particles first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were first suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are extremely light and weakly interact with other particles, making them a good candidate for dark matter. They could be made in the early universe and would still exist today, with their abundance depending on their mass. Axions are thought to be so light that they could help explain some small-scale problems in the lambda CDM model, the main cosmological model. The axion theory has gained attention in recent years, especially after WIMPs were not found. The axion's very low mass means that quantum effects could explain some of the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have formed in the very early universe, right after the Big Bang. During the period of rapid expansion called inflation, extremely dense areas of subatomic matter could have collapsed under their own gravity, creating black holes without needing a star to die, as happens with normal black holes. These black holes would exist before the first stars formed and could have masses ranging from tiny, even as small as atoms, to very large, far beyond usual stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Seldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly became popular as a possible explanation for dark matter. One advantage of primordial black holes as dark matter candidates is that the physics behind black holes is already well understood, general relativity, and black holes themselves are already known to exist. However, making primordial black holes might need special conditions, like unusual cosmic inflation or theories beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers brought renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed in the usual way, like from a star collapsing. This suggested they could be primordial. However, a study looking for signs of gravitational lensing from intermediate mass black holes, expected to be dark matter, found no evidence, although some researchers suggest this could be because of assumptions about the black hole's mass. Further observations, like those by the James Webb Space Telescope, may give more clarity on this idea. Scientists once thought that very small black holes called primordial black holes might make up a large part of dark matter. However, the Voyager 1 spacecraft, which went beyond the Sun's influence, measured the flow of positrons and electrons and found something surprising. The number of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to make up dark matter,